Every ruin has two histories. The first is the one archaeologists can reconstruct from stone, pottery, and buried foundations. The second is the one that vanished with the people who built it. Between those two histories lies a silence that has lasted for thousands of years. It is a silence filled with unfinished temples, forgotten cities, impossible masonry, and engineering that still resists complete explanation. We can uncover what was built, estimate when it was built, and sometimes even identify who built it. But understanding how and why often remains just beyond our reach. That is why the ancient world continues to fascinate us. Not because it has hidden its secrets well, but because it has allowed just enough of them to survive. The ruins of Bilbilis rise across steep limestone hills near modern Calatayud in Zaragoza province, northeastern Spain, where slopes exceeding 30 degrees create one of the most improbable Roman cities ever constructed. While travellers often remember its theatre or its connection to the poet Martial, archaeologists increasingly regard Bilbilis as an engineering achievement, whose construction methods remain only partially understood despite more than a century of excavation. The site first attracted scholarly attention during the 19th century when scattered inscriptions, architectural fragments and references in classical texts suggested the location of the Roman municipium of Augusta Bilbilis. Systematic archaeological excavations beginning in the early 20th century, followed by extensive surveys using photogrammetry, topographic mapping and architectural analysis, gradually revealed a city occupying more than 20 hectares. Instead of standing on a level plateau like many Roman colonial foundations, Bilbilis unfolded across a succession of narrow terraces, carved into a mountainside, immediately raising a question that modern archaeology still cannot answer completely. How did Roman engineers transform such unstable terrain into an urban landscape capable of supporting thousands of people for centuries? Everything begins with the mountain itself. Geological studies identify the hill as composed primarily of Jurassic limestone, overlying layers that naturally fracture and weather under seasonal rainfall. On slopes approaching or exceeding 30 degrees, gravity continuously encourages soil movement, increasing the risk of landslides and differential settlement. Modern engineers normally solve such problems through reinforced concrete retaining structures, deep foundations, computer-based slope stability models, and continuous geotechnical monitoring. Roman builders possessed none of these technologies, yet they succeeded in constructing temples, baths, houses, warehouses, administrative buildings, and one of the largest theatres in inland Hispania upon the same unstable terrain. Excavations reveal an immense system of artificial terraces rather than a simple adaptation of natural landforms. Entire sections of the mountain were cut away while other areas were built outward, using enormous retaining walls that redistributed weight across the slope. The remarkable survival of these terraces after nearly 2,000 years suggests an understanding of load transfer and hillside stabilization, far more sophisticated than surviving Roman construction manuals describe. That observation naturally leads to another mystery surrounding the retaining walls themselves. Many remain standing despite centuries of erosion, earthquakes, seasonal temperature variation, and repeated human occupation. Their stability cannot be explained merely by the strength of Roman concrete, because much of the supporting system depends upon carefully positioned limestone blocks, working together with fills of crushed stone and compacted material behind the walls. Archaeologists have identified the visible structures, but the complete construction sequence remains uncertain because temporary scaffolding, timber supports, drainage channels, and measuring equipment disappeared long ago. Without those missing elements, researchers can reconstruct only the finished result, not the practical engineering decisions that made the project possible. As the city expanded across multiple elevation levels, another challenge emerged. Every additional building increased pressure upon the terraces below. Excavation beneath several structures has revealed layered foundation systems consisting of large stones, smaller aggregate and compacted fills designed to distribute weight gradually into the hillside rather than concentrating stress at individual points. Similar principles remain fundamental in modern geotechnical engineering, yet no surviving Roman document explains how builders determined the thickness, composition, or sequence of these foundation layers. Their decisions appear remarkably consistent throughout Bilbilis, implying standardized technical knowledge that has largely vanished from the historical record. The famous theatre demonstrates this mastery even more clearly. Archaeological measurements indicate that it could accommodate approximately 4,500 spectators, making it one of the largest public structures in the region. Rather than constructing the entire cavea above ground, Roman engineers excavated portions directly into the mountain while supporting other sections with artificial substructures where natural rock was insufficient. This hybrid solution minimized material requirements while exploiting the mechanical strength of the hillside itself. Yet the transition between excavated bedrock and constructed masonry demanded exceptional precision because uneven settlement would have produced cracking throughout the seating tiers. The surviving remains indicate that such structural failure never became catastrophic, although the methods used to achieve that stability remain largely speculative. Once the terraces existed, supplying water became an equally difficult problem. Bilbilis occupied elevated ground chosen for defense and visibility rather than convenience. Water therefore had to be collected, transported, and distributed uphill across changing elevations. Archaeologists have uncovered cisterns, lead pipes, stone channels, and distribution basins, demonstrating an advanced hydraulic network integrated into the urban plan. Roman hydraulic engineering is well documented elsewhere, yet Bilbilis presents unresolved questions because significant portions of its aqueduct system have disappeared. Researchers still debate the exact capture points, the complete route of water delivery, and the hydraulic pressures maintained throughout the network. Without those missing sections, the city's full water management strategy cannot yet be reconstructed with confidence. The movement of water also affected another hidden engineering problem. Rain falling on steep mountainsides rapidly accelerates erosion, threatening foundations and retaining walls alike. Excavations of exposed underground drainage channels directing runoff away from critical structures before destructive pressure could accumulate behind terrace walls. Several passages continue to function after almost 2 millennia, indicating remarkably accurate calculations of slope, gradient, and discharge capacity. Nevertheless, large portions of the drainage system remain buried beneath unexcavated sectors of the city, leaving archaeologists unable to map the complete network or determine whether it evolved through multiple construction phases. These engineering achievements become even more remarkable when considered alongside the precision of the city's urban planning. Roman surveyors relied primarily upon instruments such as the groma for establishing right angles and the chorobates for measuring level surfaces. Those tools worked effectively on open plains, yet Bilbilis offered neither level ground nor unobstructed sightlines. Despite these limitations, modern architectural surveys reveal carefully aligned streets, coordinated public buildings, and modular planning adapted to highly irregular topography. Rather than forcing an artificial grid upon the mountain, planners subtly modified Roman urban principles to fit the landscape while preserving functional relationships between civic spaces. The accuracy visible today raises an obvious question. How did surveyors maintain consistent geometric control across steep, fragmented terrain Without modern optical instruments or digital mapping, construction logistics present one final puzzle. Thousands of tons of limestone had to be quarried, transported uphill, positioned with remarkable precision, and incorporated into terraces long before powered machinery existed. No permanent construction ramps survive. No lifting equipment has been discovered, and no written account describes the methods employed specifically at Bilbilis. Archaeologists generally propose combinations of wooden sledges, rollers, cranes driven by tread wheels, ropes, and coordinated human labour, because comparable technologies appear elsewhere in the Roman world. Even so, the archaeological evidence at Bilbilis itself remains indirect. The city preserves the completed engineering, but almost none of the temporary infrastructure that allowed it to exist. Chao-Somartin stands in the mountains of western Asturias in northern Spain, rising above the Navia River valley like an ordinary hill. Yet beneath its grassy slopes lies one of the most technologically sophisticated Iron Age settlements ever discovered on the Iberian Peninsula, a place where advanced engineering, large-scale metallurgy, and carefully planned defences appeared centuries before Rome established control over the region. Its significance only became clear in the 1960s when accidental discoveries drew archaeological attention to the hill. But systematic excavations beginning in the 1990s transformed understanding of the site. Researchers uncovered successive occupation layers extending from approximately the 8th century BC through the Roman period and into the early Middle Ages. Because later construction never completely erased the earlier settlement, archaeologists were able to reconstruct more than 1,000 years of continuous technological development. Radiocarbon dating, ceramic typology, and imported Roman materials together established an unusually reliable chronological sequence, making Chao-Somartin one of the best documented Castro settlements in northwestern Spain. What immediately distinguishes the settlement is not simply its age, but the remarkable way its builders reshaped an uneven mountain summit into a stable urban platform. The natural hill consists of fractured slate and steep slopes that should have been highly vulnerable to erosion, yet its inhabitants created extensive artificial terraces capable of supporting houses, workshops, and defensive structures over many centuries. These terraces were retained by carefully constructed stone walls that still remain standing after more than 2,000 years despite repeated exposure to heavy Atlantic rainfall. Modern geotechnical engineering explains that retaining walls survive only when builders successfully balance earth pressure, drainage capacity, and structural weight. But no surveying instruments, measurement standards, or construction manuals have survived to explain how Iron Age engineers achieved such long-term stability using only local stone and manual labour. That sophisticated understanding continues inside the defensive system. Rather than relying upon a single enclosure, Chao-Somartin expanded through multiple construction phases that added new walls while preserving earlier fortifications. The resulting concentric layout forced anyone approaching the settlement to negotiate narrow passages, abrupt turns, and elevated gateways before reaching the interior. Archaeologists have noted that these controlled access routes dramatically reduced the effectiveness of a direct assault while exposing attackers to defenders positioned above them. Similar defensive principles later became common in Roman military architecture, yet Chao-Somartin demonstrates that comparable concepts already existed among indigenous communities centuries earlier. Whether these solutions emerged independently or developed through long-distance cultural exchange remains impossible to determine, because no written records describe the design process. As excavation moved deeper into the settlement, however, the greatest surprise appeared not inside the walls, but within the industrial quarter. Archaeologists uncovered furnaces, slag deposits, tuyere fragments, charcoal concentrations, and specialized working areas that revealed an unexpectedly advanced metallurgical industry operating long before Roman administration arrived. Chemical analysis of slag demonstrated repeated smelting of both iron and copper alloys, indicating that metal production was not an occasional household activity, but a permanent and organized industry. Producing a workable iron requires furnace temperatures approaching 1200 degrees Celsius, conditions impossible to maintain without carefully controlled airflow, fuel management, and furnace geometry. Experimental archaeology has shown that even slight changes in oxygen supply dramatically affect bloom quality, yet the organic bellows, wooden supports, and leather equipment that once powered these furnaces disappeared long ago. What remains are only the vitrified furnace walls and metallic waste, proving that the technology functioned successfully. Researchers therefore understand the final products remarkably well, while still lacking direct evidence explaining exactly how craftsmen regulated combustion so consistently. Even more intriguing, metallurgical debris indicates repeated production over generations, implying that highly specialized technical knowledge survived through apprenticeship, despite the absence of written manuals or formal engineering texts. The settlement reveals another engineering achievement through a structure known as a Castro sauna, one of the most distinctive architectural traditions of northwestern Iberia. Unlike the monumental bathhouses later introduced by Rome, these buildings consisted of carefully arranged chambers where heated stones generated dense steam after water was poured onto their surfaces. Excavation identified stone-lined passages, combustion areas, and ventilation features that suggest deliberate control of airflow and temperature rather than simple heating. Archaeologists continue debating whether these facilities serve ritual purification, medical treatment, warrior initiation, or a combination of all three. Whatever their purpose, maintaining usable steam inside an enclosed stone chamber without filling it with dangerous smoke required practical knowledge of heat transfer, ventilation, and structural durability that exceeded what is usually associated with small Iron Age communities. Water management throughout Chausa Martin presents another unresolved puzzle. Mountain settlements normally suffer from rapid runoff capable of undermining foundations and triggering landslides, especially under the high annual rainfall typical of Atlantic Spain. Excavations instead revealed channels, drains, and carefully graded surfaces directing water away from buildings before it could accumulate beneath retaining walls. Modern hydraulic engineering recognizes that even small errors in drainage design eventually produce catastrophic structural failure. Yet many of these systems continued functioning for centuries, because almost all measuring tools were made from perishable materials. Archaeologists still cannot determine how builders establish consistent gradients across irregular terrain with such remarkable precision. The organization of the settlement itself also challenges traditional assumptions about Iron Age societies. Residential buildings, industrial workshops, defensive sectors, and ceremonial spaces occupy distinct areas connected through an orderly circulation network rather than developing randomly over time. This pattern suggests coordinated planning extending beyond individual households into community-wide decision-making. Similar planning principles appear elsewhere across the Castro culture, but Chausa Martin preserves them with exceptional clarity because successive occupations remained remarkably well stratified. Even so, the identity of the planners remains completely unknown. No inscriptions record political leaders, architects, or master builders responsible for organizing construction on such a scale. The history of the settlement took an unexpected turn during the Roman period, when it continued to prosper instead of disappearing immediately after conquest. Imported ceramics, Roman goods, and changing architectural styles demonstrate integration into the imperial economy while preserving elements of local tradition. That continuity ended abruptly during the 2nd century AD, when geological evidence indicates that a powerful earthquake likely damaged the settlement beyond recovery. Collapsed walls, crushed structures, and sudden abandonment preserved entire sections beneath layers of debris, creating an archaeological time capsule that has allowed researchers to reconstruct technologies normally erased by later rebuilding. Anamurium sits on the southern coast of Turkey, facing the open Mediterranean where salt, earthquakes, humidity and pirate raids should have erased an ancient city long ago. But Anamurium refused to disappear. Beneath collapsing arches and silent bathhouses lies evidence of engineering, materials and chemical knowledge that still challenge archaeologists today. The ruins were first systematically documented in the 19th century, but major excavations accelerated during the 1960s under Canadian archaeologist Elizabeth Rosenbaum. What researchers uncovered was not just another Roman coastal settlement. They found one of the best preserved necropolises in Anatolia, sophisticated water systems, unusually durable building materials, and mosaics whose colours survived nearly 2 millennia of Mediterranean sunlight and sea air. The deeper excavations went, the stranger the city became. One of the first mysteries involves survival itself. Anamurium stands directly beside the sea in a region exposed to constant humidity and salt-laden winds. Modern reinforced concrete near coastlines can begin deteriorating within decades as chloride ions penetrate the material and corrode internal structures. Yet many of Anamurium's walls, cisterns and bath complexes remain structurally stable after nearly 1,700 years. Some Roman maritime concrete structures in Italy, such as those at Pozzuoli, are known to strengthen over time through chemical reactions involving volcanic ash and seawater. But Anamurium is hundreds of kilometers away from the major volcanic zones traditionally associated with that technology. Material analysis from comparable Roman coastal sites suggests builders may have used hydraulic lime mixtures containing pozzolanic compounds capable of forming rare minerals like aluminum tobermorite. These crystals increase resistance against cracking and chemical erosion. The mystery is logistical as much as chemical. If similar materials were used at Anamurium, where did they come from? Transporting specialized mineral additives across the Mediterranean would have required a remarkably organized maritime supply network at a scale historians once underestimated. The city's water system creates another puzzle. Southern Anatolia experiences long dry summers, yet Anamurium supported bathhouses, fountains, storage reservoirs, and a large urban population for centuries. Archaeologists mapped aqueduct gradients that remained astonishingly precise across uneven rocky terrain. In some sections, the slope variation is so minimal that even small errors would have stopped water flow or created destructive pressure surges. Modern gravity-fed water systems often rely on laser measurement tools to maintain similar consistency. Roman surveyors supposedly worked using simple instruments like the chorobates and groma, yet the hydraulic precision seen here rivals far later engineering systems. The mystery becomes more striking when compared to medieval Europe. In many medieval cities over 1,000 years later, sewage and water control systems remained primitive and inconsistent. Yet at Anamurium, centuries earlier, engineers maintained controlled water distribution in one of the Mediterranean's harshest coastal environments. This raises a disturbing possibility. Certain branches of practical engineering knowledge may have been partially lost after the collapse of the Roman world. The bathhouses reveal another unexplained achievement. Anamurium used hypercaust heating systems in which hot air circulated beneath raised floors and through wall cavities. Normally, coastal moisture and thermal expansion gradually destabilize these hollow floor systems. Modern concrete structures exposed to repeated thermal cycling often develop microfractures within decades. Yet portions of Anmurium's heated floors survived for over a millennium. Some structural engineers believe Roman builders may have unintentionally created early forms of flexible composite construction. Their mortar mixtures sometimes contain crushed ceramics, volcanic particles, lime, and varying aggregate sizes that distributed stress more efficiently than rigid modern cement. Ironically, some modern Portland cement structures degrade faster because they are too rigid under environmental stress. In certain ways, Roman materials behaved less like brittle stone and more like adaptive geological systems. Then there is the necropolis, one of the largest surviving Roman cemeteries in Anatolia. Hundreds of tombs spread across unstable coastal terrain, vulnerable to erosion and seismic activity. Yet many remain standing despite centuries of earthquakes affecting the eastern Mediterranean. Geological studies suggest some structures distributed weight unusually well across softer soil layers instead of anchoring deeply into rigid foundations. Modern earthquake-resistant architecture often relies on controlled flexibility rather than absolute rigidity. Japanese seismic engineering, for example, allows buildings to absorb and redistribute movement rather than resisting it completely. The unsettling question is whether ancient builders discovered similar principles empirically through generations of observation. If so, Anamurium may preserve evidence of forgotten seismic adaptation techniques developed nearly 2,000 years before modern structural dynamics emerged as a scientific discipline. But perhaps the strangest mystery of all appears inside the city's surviving mosaics and pigments. At first glance, the mosaics seem merely decorative. Geometric floors, coloured stone patterns, fragments of wall paintings. But laboratory examinations reveal something deeply unusual about their durability. The Mediterranean climate is brutally destructive to pigments. Ultraviolet radiation breaks molecular bonds. Salt crystallization fractures surfaces internally. Humidity accelerates chemical reactions that bleach ancient colours. Even many medieval frescoes deteriorated rapidly under such conditions. Yet some pigments at Anamurium retained remarkable chromatic stability after nearly 2,000 years. Researchers studying Roman pigments across the Mediterranean identified compounds containing iron oxides, Egyptian blue, cinnabar, carbon black, and copper-based minerals capable of resisting extreme environmental degradation. Egyptian blue is especially mysterious. First synthesized over 4,500 years ago, it is considered humanity's earliest synthetic pigment. Modern scientists discovered that it emits infrared luminescence invisible to the human eye, a property now being explored for anti-counterfeit technologies and advanced imaging systems. What makes this disturbing is not merely that ancient civilizations created durable pigments. It is that some of these manufacturing methods remain incompletely understood even today. Reproducing exact ancient pigment compositions consistently has proven difficult because tiny variations in temperature, mineral purity, kiln atmosphere, and particle size dramatically affect the final chemical stability. At Anamurium, several mosaic fragments survived conditions that should have erased them centuries ago. In some protected areas, pigment adhesion remained unusually strong despite prolonged salt exposure. Certain mineral combinations appear to have formed microscopically stable crystalline bonds with plaster surfaces, reducing flaking and moisture penetration. In modern conservation science, researchers still struggle to develop restoration materials capable of matching the longevity of some Roman pigments. The comparison becomes even more uncomfortable when viewed against modern architecture. Many contemporary paints begin fading within years under ultraviolet exposure. Some modern coastal concrete structures require major restoration after only 50 to 100 years. Meanwhile, ancient pigments at Anamurium endured nearly 20 centuries of sea air, storms and heat, while preserving visible colour integrity. This pattern appears repeatedly across the ancient world. Roman concrete outlasting modern seawalls, Egyptian pigments resisting ultraviolet decay longer than industrial paints, ancient hydraulic systems maintaining stable gradients without electronic instruments. Again and again, archaeology uncovers technologies that seem primitive according to historical narratives, yet perform at levels surprisingly difficult to replicate. Do you think civilizations like Anamurium truly possessed engineering knowledge far beyond what history tells us? Or are modern scientists still underestimating the capabilities of the ancient world? Share your thoughts in the comments below. Located beneath the modern cities of Izumi and Izumiotsu in Osaka Prefecture, Japan, Ikegami-Sone appears at first to be an ordinary archaeological site, yet beneath the soil lies evidence of engineering so sophisticated that archaeologists still cannot fully explain how it was achieved nearly 2,000 years ago. The site was identified in the early 20th century, but its true importance emerged after large-scale excavations beginning in the 1970s uncovered one of the largest Yayoi settlements ever discovered. Covering more than 60 hectares and occupied from approximately the 1st century BCE to the 3rd century CE, Ikegami-Sone revealed hundreds of buildings, defensive ditches, workshops, storage facilities, and one extraordinary wooden structure unlike anything previously known from the Yayoi period. Among all the discoveries, nothing has generated more debate than the enormous pillar foundations standing near the centre of the settlement. Archaeologists uncovered two massive post holes, measuring nearly 2 meters in diameter, each originally supporting a gigantic wooden column cut from camphor trees. Analysis of the post holes and preserved timber indicates that each trunk measured roughly 70 to 90 centimeters across, while reconstruction suggests the columns may have risen more than 10 meters above the ground and perhaps even approached 15 meters. Such dimensions immediately raise a difficult engineering question, because no written record survives to explain what kind of building required supports of this scale. Some researchers interpret the structure as a ceremonial tower visible across the surrounding plain. Others suggest an elevated granary, a monumental gateway, or the foundation of a large administrative building. Yet none of these theories fully explains why only 2 enormous pillars were necessary. Without surviving upper architecture, the purpose of the structure remains one of the greatest unresolved mysteries of prehistoric Japan. That uncertainty becomes even greater when considering the practical challenge of construction. A mature camphor tree with a trunk approaching 1 meter in diameter can weigh many tons before processing, and even after trimming, transporting such timber without iron machinery, wheeled transport capable of carrying extremely heavy loads, or draft animals on a large scale would have required remarkable organization. Archaeologists have proposed the use of wooden rollers, ropes woven from plant fibers, earthen ramps and coordinated human labor, but no direct archaeological evidence has revealed the actual construction method. Unlike Egyptian pyramids or Roman monuments, no construction tools, transport tracks, or unfinished lifting systems have been preserved. The builders clearly possessed techniques capable of solving these logistical problems, yet those techniques disappeared without leaving written instructions, forcing modern researchers to reconstruct the process largely through experimental archaeology. Even more remarkable is the deliberate choice of camphor wood itself. This decision appears far too sophisticated to have been accidental. Camphor trees produce natural aromatic compounds that resist insects and fungal decay, making the timber exceptionally durable in Japan's humid climate. The wood also possesses considerable structural strength while remaining relatively resistant to splitting during long-term use. Selecting such material implies that Yayoi builders possessed accumulated empirical knowledge about the mechanical behavior of different tree species, understanding not only which woods could support enormous vertical loads, but also which could survive decades or even centuries under constant exposure to moisture. What remains unexplained is how this knowledge developed. No surviving documents describe forestry management, timber classification, or construction manuals from the Yayoi period because writing had not yet become established in Japan. The expertise must therefore have been transmitted through generations of craftsmen entirely by observation and practice. Modern engineers can explain why camphor performs well as a structural material, but they cannot determine how prehistoric builders acquired such advanced practical knowledge without formal scientific methods. The enormous pillars at Ikegami-Sone therefore represent not only an architectural mystery, but also a lost tradition of material engineering whose origins remain invisible. This sophisticated understanding of materials appears throughout the settlement itself. Excavations reveal that Ikegami-Sone was not an irregular village expanding randomly over time, but a carefully organized community with residential districts, workshops, storage buildings, ritual spaces and open areas arranged according to an overall plan. Several rows of buildings follow consistent orientations, suggesting deliberate surveying before construction began. Creating such an organized settlement across more than 60 hectares would have required accurate measurement, planning and coordination among large numbers of workers. Yet archaeologists have recovered no standardized measuring rods, surveying instruments, or construction drawings capable of explaining how this precision was achieved. The regularity suggests that builders relied upon established systems of proportion and alignment that have completely vanished from the archaeological record. The location itself introduces another engineering puzzle. Osaka's lowlands are characterized by soft alluvial sediments deposited by rivers over thousands of years, conditions that normally complicate the construction of heavy timber structures. Massive wooden columns placed directly into unstable ground would gradually lean or sink as the soil compressed beneath them. Excavation, however, indicates that the giant post holes were prepared with exceptional care before the columns were installed. Their depth, shape, and surrounding soil suggest that builders understood the importance of creating stable foundations capable of distributing enormous loads. Whether they intentionally compacted the ground, added gravel, improved drainage, or employed another technique remains uncertain because organic evidence rarely survives after nearly 2 millennia. Nevertheless, the stability implied by these foundations demonstrates practical geotechnical knowledge far beyond what is often assumed for prehistoric farming communities. Water management throughout Ikegami-Sone presents another example of unexpected technical ability. The settlement occupied a region vulnerable to seasonal rainfall, yet excavations uncovered networks of ditches, drainage channels, and carefully elevated construction platforms that reduced flooding around important buildings. Rather than relying upon stone-lined canals or hydraulic cement, the inhabitants shaped the landscape itself, controlling runoff through subtle changes in elevation and interconnected earthworks. Such systems required long-term observation of rainfall patterns, groundwater movement, and seasonal flooding. Their success is demonstrated by the settlement's continuous occupation for several centuries despite challenging environmental conditions. Exactly how these drainage systems were designed without written calculations or permanent engineering institutions remains unknown. The settlement also functioned as a major production center rather than a simple farming village. Archaeologists discovered evidence of woodworking, stone tool manufacture, pottery production, weaving and bronze casting, indicating a highly specialized economy supported by skilled craftspeople. Such industrial diversity implies organized labor, reliable food storage, and administrative coordination capable of sustaining specialists who were not directly engaged in agriculture. Yet no palace, archive, or written administrative record has ever been found. The existence of complex economic management is therefore inferred entirely from physical evidence, leaving historians unable to identify the individuals or institutions responsible for directing such an advanced community. Perched almost 100 meters above the Bay of Biscay near modern Gijón in Asturias, northern Spain, La Campa Torres appears at first to be another Iron Age hill fort overlooking the Atlantic. Yet beneath its windswept cliffs lies evidence of engineering decisions so sophisticated that archaeologists are still debating how an indigenous community, more than 2,000 years ago, transformed an exposed rocky headland into one of the strongest fortified settlements along the Cantabrian coast. The site remained hidden beneath later occupation until systematic archaeological excavations began during the 1980s, after surveys identified prehistoric pottery, defensive earthworks, and structural remains scattered across the headland. Excavations revealed continuous occupation beginning around the Late Bronze Age, with major expansion during the Iron Age by the Astures before the Romans established military and commercial facilities on the same promontory after the Cantabrian Wars. Stratigraphic analysis, radiocarbon dating of organic remains, imported ceramics and Roman materials consistently placed the principal indigenous settlement between approximately the 4th and 1st centuries BC, confirming that its most remarkable engineering achievements predated direct Roman administration. Once the settlement emerged from the ground, researchers realized that its greatest achievement was not the massive walls themselves, but the extraordinary way the builders adapted every structure to an unforgiving landscape. The headland consists of fractured sandstone and quartzite continuously exposed to Atlantic storms, salt spray, intense rainfall, and powerful winter winds that frequently exceed 100 kilometers per hour. Building permanent fortifications on such terrain would normally accelerate erosion and structural instability, yet substantial sections of defensive walls, terraces, and building platforms have survived for more than 2 millennia. Geological studies indicate that the builders repeatedly cut directly into bedrock before laying foundations, reducing differential settlement while using the natural contours to distribute structural loads instead of fighting against the terrain. Although modern engineers can explain why these solutions work mechanically, archaeologists still cannot determine how Iron Age builders acquired such practical geological knowledge without written engineering traditions or surviving technical manuals. The defensive system itself demonstrates an equally impressive understanding of terrain. Excavation has revealed multiple defensive components including ditches, ramparts, stone walls, and carefully controlled entrances that forced anyone approaching the settlement to climb uphill while repeatedly changing direction. Modern battlefield analysis recognizes this arrangement as an effective method for reducing the momentum of attacking forces while maximizing the advantage of defenders occupying higher ground. Computer-based visibility studies conducted on similar Atlantic hillforts have shown that elevated coastal settlements could monitor extensive stretches of shoreline, allowing early detection of ships long before they reached land. La Campa Torres occupies exactly such a commanding position, suggesting that its builders selected the location not only for defense, but also for surveillance of maritime traffic across the Bay of Biscay. Whether this strategic placement resulted purely from accumulated experience or from systematic observation remains impossible to determine, because no written records survive from the Astures themselves. As excavation expanded across the interior, however, archaeologists encountered a mystery that continues to attract particular attention. Instead of houses appearing randomly wherever space permitted, many residential structures occupy remarkably consistent plots arranged according to repeated spatial patterns. Individual buildings differ in detail, yet their dimensions, spacing, and orientation display a surprising degree of regularity, despite the irregular shape of the rocky plateau. Excavation plans reveal that walls frequently align along common axes, while open spaces between buildings remain relatively uniform, even where the terrain changes dramatically. Such consistency strongly suggests that construction followed predetermined planning principles rather than spontaneous expansion over generations. This apparent modular urban planning raises difficult questions because none of the tools normally associated with standardized surveying have been discovered. No measuring rods, calibrated markers, engraved plans, or written instructions have been recovered from the site. Nevertheless, repeated architectural proportions indicate that builders probably relied on standardized units transmitted through practical tradition. Experimental archaeologists have demonstrated that simple measuring cords tied with regularly spaced knots can achieve surprisingly high precision across large construction projects, yet no direct evidence confirms that such techniques were employed at La Campa Torres. If flexible cords, wooden templates, or organic measuring devices formed the basis of construction, they would have disappeared completely in the humid Atlantic environment long before excavation began. The settlement therefore preserves the finished geometry, while the instruments that created it have vanished, leaving only the pattern itself as indirect evidence of an organized planning system. The implications extend beyond architecture alone. Standardized plots suggest coordinated allocation of space, implying that someone possessed authority to determine where houses could be built before construction even began. Such organization reflects a level of social administration far more sophisticated than older interpretations of loosely organized Iron Age tribal communities. Similar planning principles have been identified at several major castros across northwestern Iberia, yet each settlement applies them differently according to local topography. This combination of standardization and adaptation hints at an engineering tradition capable of balancing fixed construction rules with changing geological conditions. Exactly how this knowledge was taught remains unknown because the Astures left virtually no written documentation explaining their building practices. Water management presents another unresolved engineering challenge. Asturias receives well over 1,000 millimeters of rainfall annually, creating continuous risks of erosion on exposed coastal slopes. Without effective drainage, heavy seasonal rain would gradually undermine retaining walls and destabilize occupied terraces. Surprisingly, excavation has revealed relatively limited evidence of catastrophic slope failure during the principal occupation period. Archaeologists believe the builders probably incorporated shallow drainage channels, permeable stone layers, and carefully controlled surface gradients that redirected runoff toward natural fissures within the bedrock. Most of these hydraulic features would have consisted partly of earth, timber, or other biodegradable materials that disappeared centuries ago, making complete reconstruction impossible. The remarkable preservation of structural foundations nevertheless indicates that water was managed far more effectively than previously assumed for communities lacking Roman hydraulic technology. Construction logistics introduced another enduring mystery. Thousands of stone blocks had to be extracted, transported across uneven ground, and positioned accurately on steep slopes where wheeled vehicles would have been of limited practical use. Archaeologists propose combinations of wooden sledges, rollers, rope systems, levers, and coordinated human labor because comparable techniques are documented elsewhere in prehistoric Europe. Even so, no quarry infrastructure, hauling ramps or construction equipment has been identified at La Campa Torres itself. The finished architecture survives, while the temporary engineering systems responsible for creating it disappeared almost without trace, forcing researchers to reconstruct the entire construction process through comparison rather than direct evidence. Excavations also uncovered iron slag, metallurgical debris and evidence of local metalworking, demonstrating that the settlement functioned as more than a military stronghold. Iron production requires furnace temperatures approaching 1200 degrees Celsius, together with carefully regulated airflow and controlled charcoal quality. Although these technological requirements are well understood today, the furnaces themselves survive only in fragmentary condition, preventing archaeologists from determining exactly how local craftsmen maintained stable temperatures or organized repeated production cycles. The existence of successful metallurgy nevertheless confirms that sophisticated practical knowledge extended beyond architecture into industrial processes. About 160 kilometers north of Luxor, near the edge of the Nile Valley Desert, lies Abydos Temple Complex, one of the oldest sacred cities in Egyptian history. Archaeologists began major excavations here during the 19th century, but the site became globally controversial after researchers uncovered the massive subterranean Osiraion structure behind the Temple of Seti first. Unlike the decorated limestone temple above it, the Osiraion was built from enormous granite blocks weighing up to 70 tons each. Its engineering appeared older, heavier, and strangely disconnected from the architectural style of New Kingdom Egypt. The deeper excavations went, the stranger Abydos became. Hidden chambers, precision-cut stone surfaces, unexplained water erosion, astronomical alignments, and controversial carvings transform the site from a religious monument into one of the greatest ancient technological mysteries ever discovered. The Osiraion is the single most mysterious structure in Abydos. Buried below ground level and surrounded by water channels, it looks dramatically different from the refined decorative temples of dynastic Egypt. Instead, it resembles the megalithic style seen at sites like Puma Punku in Bolivia or the platform stones of Baalbek in Lebanon. Its granite blocks are enormous, some weigh between 50 and 70 tons, and were transported from Aswan, over 150 kilometers away. Even today, moving stones of that size requires cranes, hydraulic systems, and carefully engineered transport platforms. Yet the Egyptians somehow moved, aligned, and fitted these blocks with astonishing precision over 3,000 years ago. What confuses researchers most is the construction quality. Many joints between stones are so tight that a modern razor blade cannot fit between them. Some surfaces appear machine polished. Others contain unusually straight internal angles rarely achieved with simple copper tools. Experimental archaeology has shown that cutting granite with copper saws and quartz sand is technically possible, but reproducing Abydos-level precision requires extraordinary labor and time. Some engineers argue the efficiency implied by the Osiraion simply does not match the accepted technology of the Bronze Age. Even stranger is the erosion. Several lower granite surfaces show patterns resembling prolonged water exposure. Geological comparisons have led some alternative researchers to suggest the Osiraion may predate dynastic Egypt entirely, possibly originating during a wetter climatic period thousands of years earlier. Mainstream Egyptology disputes this theory, yet the erosion patterns continue fueling debate. Inside the Temple of Seti first, the stonework reaches a level of refinement difficult to explain using primitive tools alone. The temple walls contain thousands of deeply engraved hieroglyphs with nearly identical depth and spacing. Columns stand with near-perfect symmetry. Flat granite surfaces show deviations of only millimeters across several meters. Granite is one of the hardest stones commonly used in ancient construction. Its quartz crystals rate around 7 on the Mohs hardness scale, while copper tools rank around 3. This means the Egyptians were technically working with tools softer than the stone itself. Modern reconstructions suggest workers may have used quartz sand as an abrasive, essentially grinding the granite rather than cutting it directly. However, the precision seen at Abydos rivals certain machine-assisted masonry techniques. Circular drilling marks discovered on some Egyptian granite artifacts elsewhere in Egypt indicate penetration rates that some engineers consider unusually high for manual drilling systems. Comparisons are often made with the Inca stonework at Sacsayhuaman or the polygonal walls of Ollantaytambo. Yet Abydos differs because many surfaces here are not only tightly fitted but geometrically uniform. Some researchers speculate the Egyptians may have possessed advanced lost techniques involving vibration-assisted cutting, chemical softening of stone, or highly specialized abrasive systems never fully documented in surviving records. Among the most famous mysteries at Abydos are the so-called helicopter hieroglyphs. Located high on a temple beam, several overlapping carvings appear to resemble a helicopter, submarine, jet aircraft, and even a tank. Mainstream Egyptologists explain the phenomenon as a palimpsest, an effect created when older hieroglyphs were plastered over and later recarved by another pharaoh. Over centuries, erosion exposed both layers simultaneously, accidentally creating modern-looking shapes. Scientifically, this explanation is reasonable, yet the controversy persists because the resemblance is remarkably specific. Millions of visitors have seen the carvings, and the images spread globally as supposed evidence of lost technology or ancient knowledge. What makes the debate more interesting is not necessarily the carvings themselves, but what they represent psychologically. Abydos repeatedly confronts researchers with structures and engineering choices that already feel technologically advanced. The helicopter hieroglyphs became symbolic of a larger question: how much ancient knowledge has truly been lost? The layout of Abydos appears deeply connected to astronomy. The temple axis aligns with celestial patterns associated with Osiris, often linked symbolically to the Orion constellation. Ancient Egyptian texts repeatedly connect the soul of the pharaoh with stars in Orion's belt. During specific times of the year, sunlight travels through dark corridors and illuminates interior chambers with striking accuracy. Achieving this effect required careful calculations involving solar angles, seasonal movement, and architectural orientation. This phenomenon can also be seen at Abu Simbel, where sunlight reaches the inner sanctuary only twice per year, and at Newgrange in Ireland, where the winter solstice sun penetrates a narrow stone passage precisely at dawn. Yet Abydos contains a more labyrinth-like internal design, making its alignments especially difficult to engineer. Some archaeoastronomers argue that ancient builders possessed observational astronomical knowledge far beyond what is commonly assumed. Without telescopes or modern instruments, they tracked celestial movement accurately enough to orient massive stone complexes over long distances with minimal error. Several chambers inside Abydos produce unusual acoustic effects. Deep sounds resonate for extended periods, and low frequencies appear amplified within enclosed stone rooms. Visitors often describe a heavy vibrating sensation when speaking inside certain sections of the Osirion. Acoustic specialists studying ancient monuments have noted similar effects in Malta's Hippogeum, the Mayan pyramid at Chichen Itza, and Neolithic passage tombs across Europe. In some structures, specific frequencies can alter human perception, concentration, and emotional response. The granite used in the Osirion may also contribute to resonance behavior. granite contains quartz crystals capable of piezoelectric effects under pressure, although no evidence proves the Egyptians intentionally used this property technologically. Still, the repeated appearance of resonance chambers in sacred ancient sites has led some researchers to question whether sound played a larger ritual or psychological role in ancient civilizations than previously believed. Modern ground-penetrating radar surveys around Abydos have revealed buried anomalies beneath the surface, including linear formations and possible voids near the Osirion. Some archaeologists believe entire sections of the ancient sacred city remain hidden beneath layers of Nile sediment. This possibility is significant because Abydos was continuously occupied and rebuilt over thousands of years. Like Troy or Jerusalem, newer civilizations repeatedly constructed temples atop older foundations. If deeper layers exist, they could potentially preserve structures from Egypt's earliest dynastic periods, or perhaps even older unknown phases of occupation. Satellite archaeology has already transformed Egyptian exploration in recent decades. Infrared imaging has revealed buried settlements, lost pyramids, and hidden road systems elsewhere across Egypt. Abydos may still conceal major discoveries waiting beneath the desert floor. One of Abydos' most historically important discoveries is the Abydos King List, a chronological sequence of pharaohs carved into the temple walls. Yet several rulers are deliberately missing, including Akhenaten, Tutankhamun, and other controversial figures connected to religious upheaval. This was not an accident. Ancient Egyptian rulers intentionally edited history. Pharaohs considered illegitimate or dangerous were removed from official records in an attempt to erase their memory entirely. The practice reveals something unsettling about ancient civilizations. Historical records were controlled narratives, not objective archives. If entire rulers could disappear from official inscriptions, researchers must ask how much additional knowledge vanished over the centuries. Do you think the mysteries of Abydos temple complex prove that ancient civilizations possessed lost knowledge far beyond what modern history accepts? Share your thoughts in the comments below. Perched above the Alhama River in La Rioja, northern Spain, Contrebia-Lucard may at first seem like just another ruined Iron Age hill fort, yet beneath its weathered cliffs lies one of the most remarkable engineering landscapes created by the Celtiberians. Long before Roman rule reached this region, an entire fortified city was carved directly into living sandstone, leaving behind construction methods that archaeology can describe but still cannot fully explain. The ruins were known locally for centuries, but systematic archaeological investigation only began during the 20th century, with extensive excavations from the 1970s onward, revealing streets, defensive systems, reservoirs, dwellings, and public spaces preserved beneath accumulated sediment. Stratigraphic analysis, ceramic typology, and Roman historical sources indicate that the settlement flourished between approximately the 4th century BCE and the 1st century BCE, before gradually declining after Roman control of the region became firmly established. Every excavation season has exposed additional evidence that the visible ruins represent only part of a far larger urban plan, concealed within the rock itself. What immediately separates Contrebia-Lucard from nearly every other Celtiberian settlement is that its builders did not simply construct on top of a mountain. They reshaped the mountain into the city. Instead of leveling the summit with imported fill or raising massive masonry platforms, they transformed the natural sandstone bedrock into streets, stairways, building foundations, storage chambers, drainage channels, and defensive features by removing enormous quantities of solid rock. Modern archaeologists can measure the finished surfaces with remarkable precision, but they still cannot reconstruct exactly how Iron Age engineers achieved such extensive modification using the technology available more than 2,000 years ago. Sandstone is softer than granite, yet it remains a durable sedimentary rock that demands sustained labour, accurate planning and effective tools to produce long, flat surfaces across an entire settlement. This raises one of the site's greatest mysteries. Every street appears to belong to a coordinated urban design rather than centuries of random expansion. Pathways connect residential districts with storage areas, defensive sectors and water facilities while following gradients that remain practical even today. Such organisation suggests that the builders possessed a comprehensive master plan before excavation even began. Unlike Roman colonies, however, no written plans, surveying manuals or administrative records survive to explain how measurements were transferred across the irregular mountain surface. Historians assume that ropes, wooden stakes, simple levelling instruments, and accumulated practical experience guided the work, yet none of these temporary construction systems have survived in the archaeological record. What remains is the finished geometry, while the engineering process itself has almost completely disappeared. As researchers continued examining the settlement, another remarkable achievement emerged from beneath the rock. Much of the city's infrastructure was integrated directly into the same sandstone mass, instead of being added afterward. Reservoirs, cisterns, wells, and narrow channels were carefully carved into the bedrock to collect and distribute water throughout the settlement. Northern Spain experiences highly seasonal rainfall, making reliable storage essential for survival during dry periods and prolonged military sieges. Hydrological studies indicate that several channels were designed with gradients gentle enough to maintain water flow while minimizing erosion, demonstrating practical knowledge of hydraulic behavior. Although the principles involved can be explained scientifically today, archaeologists still debate how Iron Age builders calculated these gradients across an uneven landscape without modern surveying equipment. Their success becomes even more impressive because portions of the drainage network continue directing rainwater efficiently after more than 2 millennia of natural weathering. The defensive system surrounding Contrebia Leucidae adds another layer to the engineering puzzle. Rather than relying solely on masonry walls, the inhabitants excavated a monumental rock-cut ditch separating vulnerable approaches from the fortified plateau. Archaeological surveys estimate that this trench extended for nearly 700 metres, reaching widths of roughly 8 to 9 metres and depths approaching 8 metres in some sections. Excavating such dimensions required removing tens of thousands of cubic metres of sandstone. Experimental archaeology demonstrates that iron chisels and hammers are capable of cutting sandstone, but reproducing a ditch of this scale would require an enormous labour force working continuously for years. Surprisingly, archaeologists have not identified equally massive spoil deposits nearby. The missing waste rock has generated several hypotheses. Some researchers believe much of the excavated material was reused for construction elsewhere within the settlement, while others suggest centuries of erosion dispersed the debris downslope. Neither explanation fully accounts for the quantity of stone that must originally have been extracted. Roman historians provide additional context for the city's formidable reputation. Titus Livius, better known as Livy, described campaigns in Celtiberia during the 2nd century BCE in which fortified settlements repeatedly resisted Roman armies, despite their superior military organization. Although historical accounts must always be interpreted carefully, archaeological evidence confirms that Contrebia Leucidae possessed one of the most sophisticated defensive layouts in the region. Attackers approaching the settlement would have encountered narrow access routes, elevated observation points, steep natural cliffs, and the immense rock-cut ditch before reaching the main fortifications. The surrounding landscape itself became part of the defensive architecture, demonstrating an understanding that terrain could be engineered as effectively as walls. Equally fascinating is the city's sophisticated approach to controlling water during storms. Rain falling across the plateau did not simply erode buildings or accumulate unpredictably. Instead, carefully carved channels redirected runoff toward designated collection points while protecting residential areas from destructive flooding. Modern geomorphological analysis shows that erosion patterns around many excavated sectors remain surprisingly limited considering more than 2,000 years of exposure. Such preservation reflects not only the durability of sandstone but also the effectiveness of the original drainage design. Whether these systems resulted from generations of practical experimentation or from highly specialized engineering knowledge passed between craftsmen remains unknown because no written Celtiberian technical texts have ever been discovered. Construction logistics remain perhaps the most difficult question of all. Every surface visible today represents the final stage of an immense engineering project, yet almost every temporary element required to complete that project has vanished. Wooden scaffolding decays, rope disappears, measuring stakes rot, and earthen working platforms erode into the landscape. Archaeologists, therefore, study negative evidence, attempting to reconstruct vanished construction methods solely from finished stonework. Tool marks preserved on some carved surfaces indicate repeated impact from iron implements, but they cannot reveal workforce organization, construction schedules, or management techniques. Large-scale public works require planning, food supplies, skilled supervision, and coordinated labor, suggesting that Contribia Lucard possessed a social organization considerably more sophisticated than its surviving material culture alone might imply. Excavations found imported pottery, local ceramics, metal items, and other objects, showing the city was part of wide trade networks across Iberia and the Western Mediterranean. Its people weren't isolated, but trade alone doesn't explain why its engineering is so different. While rock-cut features exist elsewhere, nowhere else forms a whole city carved so deeply into stone, leaving the origins of this knowledge still unclear. High above the dense forests of western India, rising nearly 700 meters into the sky, the staircase of Kalavantin-Durg cuts into a near-vertical wall of basalt, and at first glance, it looks like a path dangerous, narrow, intimidating, but the longer you study it, the more it begins to resemble something else entirely, a technical paradox carved into stone, because this is not simply a staircase. It is a construction problem that modern engineering can explain only in fragments, a structure that exists physically, yet resists complete reconstruction in theory, as if the process that created it has been erased, while the result remains suspended in time. The first documented surveys of Kalavantin-Durg by British colonial officers in the 19th century treated the structure as a defensive hill fort, likely associated with regional powers such as the Marathas, and early descriptions focused on its strategic value, its commanding view over ancient trade routes, and its natural isolation. Yet even in those early reports, one detail stood out with unusual intensity. The steps, carved directly into the rock face, ascending at angles approaching 70 to 80 degrees, in several sections narrowing to less than half a meter in width, with no railings, no anchors, no visible sockets for scaffolding, only a sequence of carefully cut footholds rising into open air, defying not only comfort but expectation, because even today, standing at the base and looking up, it is difficult to imagine not just climbing them but creating them. Subsequent archaeological attention, particularly throughout the 20th century, shifted toward material analysis and comparative study, revealing that the rock itself belongs to the Deccan Traps, a massive volcanic formation composed primarily of dense basalt, known for its strength and resistance to erosion. And through field testing alongside comparisons with nearby monumental sites such as Ellora Caves, researchers confirmed that ancient Indian craftsmen possessed the necessary tools, iron chisels, hammerstones, and controlled percussion techniques to cut and shape this material with remarkable precision, as demonstrated by Ellora, where entire multi-story temple complexes were carved downward from solid rock with alignment accuracy measured in centimeters. Yet Kalavant in Durg introduces a critical variable absent from those sites, because while Ellora was carved from stable horizontal working surfaces with predictable access, here the work surface is a near vertical cliff, a plane where balance, positioning, and even survival become uncertain variables, and that single difference transforms a known capability into an unresolved mystery. Later field measurements conducted by trekking groups and independent surveyors documented the geometry of the staircase in greater detail, showing that while the steps are not perfectly uniform, they follow a consistent functional pattern, with tread depths averaging between 15 and 20 centimeters, just sufficient for a human foothold and riser heights, adapting dynamically to the natural contours of the rock while still maintaining a climbable rhythm, suggesting that the builders were not carving randomly but were instead following an intentional system, a logic embedded into each cut. And this level of consistency implies coordination among multiple workers, shared understanding of spacing, and possibly even a conceptual design before execution. Yet despite this apparent organization, no inscriptions, no quarry marks, no tool signatures, and no construction diagrams have ever been discovered, leaving behind only the completed form without any surviving evidence of the method that produced it. And it is here, at the level of method, that the mystery becomes most resistant to explanation, because while the material can be identified and the geometry can be measured, the process itself remains hidden. And one widely discussed hypothesis suggests that the staircase was carved from the top downward, meaning that workers first reached the summit by an alternative route, perhaps a natural ridge or slope that has since eroded away, and then progressively cut the steps as they descended, a technique that aligns with known practices at other rock-cut sites across India. Yet this hypothesis immediately encounters a critical contradiction, because extensive surveys of the surrounding terrain have failed to identify any viable ancient access path capable of supporting the movement of tools, labor, and materials to the summit, with the slopes around Kalavantin remaining steep, unstable, and in many areas effectively inaccessible even to modern climbers without specialized equipment, raising the possibility that the original access route, if it existed at all, has been completely lost to geological time. A second hypothesis proposes the construction of wooden scaffolding rising from the base of the cliff, suggesting that temporary frameworks made from timber could have provided platforms for workers to stand on while carving each step upward in sequence. Yet this theory too faces significant challenges, as no archaeological evidence of such scaffolding has been found, no post holes drilled into the rock, no anchor points, no remnants of organic material preserved in crevices, and beyond the absence of evidence lies a deeper structural question. Because the cliff face is exposed to strong seasonal monsoon winds and intense rainfall, conditions that would place enormous stress on any wooden structure attempting to cling to such a vertical surface, making the long-term stability of such scaffolding highly questionable. A third line of speculation explores the possibility of rope-based construction techniques, where workers may have used fiber ropes, primitive harness systems, or bodyweight anchoring methods to suspend themselves against the rock while carving, drawing loose parallels with certain traditional climbing practices observed in isolated cultures. Yet this hypothesis remains speculative at best, as no tools, no visual depictions, and no surviving artifacts directly connect such methods to the builders of Kalavantin-Durg. And even if such techniques were employed, they do not fully resolve the core problem. Because while it is possible to climb a vertical surface using ropes, the act of carving consistent, load-bearing steps into hard basalt while suspended in mid-air introduces a level of complexity that even modern climbers with advanced gear and safety systems rarely attempt, and certainly do not perform with the precision observed here. When placed alongside other ancient rock-cut achievements, the uniqueness of Kalavantin becomes even more pronounced, because at Petra, monumental structures were carved into sandstone cliffs but relied on ledges and constructed platforms that provided stable working conditions. And at Machu Picchu, steep stairways were integrated into mountainous terrain, yet supported by terraces and retaining walls that distributed weight and provided access. Whereas Kalavantin-Durg eliminates these supporting systems entirely, isolating the act of carving from any stable base, reducing the process to a direct interaction between human and vertical stone. And it is precisely this isolation that makes the site so difficult to reconcile with known construction methodologies. Time itself adds another layer to the puzzle, as erosion patterns indicate that the steps have endured for several centuries, possibly dating back to medieval periods or earlier, with edges worn yet still structurally intact. And despite continuous exposure to heavy rainfall, temperature variation, and natural weathering, the staircase remains usable, suggesting that the builders not only understood how to cut basalt, but also how to select sections of rock less prone to fracturing, working with the natural grain and internal structure of the material to maximize durability, an insight that implies accumulated knowledge rather than isolated experimentation. Yet no intermediate stages of development have been identified, no abandoned staircases, no incomplete sections, no gradual evolution of technique, leaving Kalavantin to appear in the historical record as a fully realized concept without visible precursors. Perhaps the most unsettling aspect of this entire structure lies not in what has been discovered, but in what remains absent, because archaeology depends as much on process as it does on outcome. And here, the process is missing, leaving only a finished artifact that suggests a sequence of actions we cannot fully reconstruct. With each proposed explanation containing gaps, each theory relying on assumptions that cannot be verified, and in that absence, the staircase becomes more than a physical object. It becomes a boundary marker, defining the limits of current understanding. Kalavantin-Durg forces that boundary into focus, suggesting that ancient builders may have possessed not only the physical capability to shape hard volcanic stone, but also the spatial awareness, coordination, and adaptive strategies required to operate in environments that remain challenging even today, challenging the modern assumption that complex construction is inseparable from advanced technology, and raising a possibility that is difficult to dismiss, that the limitations we attribute to ancient engineering may reflect gaps in our interpretation rather than gaps in their ability. In your opinion, how was the Kalavantin-Durg staircase built under such seemingly impossible conditions? Share your thoughts in the comments below. A. In 1800, British surveyor Colin Mackenzie began documenting the ruins of Vijayanagara at Hampi in the present-day Indian state of Karnataka. Among the remains inside the royal centre stood an enormous terraced platform later identified with a ceremonial structure described by 16th century Portuguese visitors. Today it is known as the Mahanavami Dibba, the great platform from which Vijayanagara's rulers displayed imperial power before thousands of spectators. The surviving monument rises more than 10 meters above its surroundings and consists of 3 ascending levels, each faced with carefully assembled masonry and bands of carved reliefs. Its position was deliberately commanding. The platform occupied one of the highest points in the royal zone, overlooking spaces where processions, military reviews, animal displays, dances, and ceremonial gatherings could take place. Yet what visitors see today is only the stone base. Archaeological interpretation suggests that a pillared wooden pavilion once stood on the summit, but almost every trace of that superstructure disappeared when Vijayanagara was conquered and devastated in 1565. The engineering puzzle therefore begins with an incomplete building whose most important upper section has vanished. The platform was not constructed in a single operation. Architectural analysis indicates at least 3 major building phases extending across the Vijayanagara period. Earlier masonry was enlarged, covered or incorporated into later additions, producing the stepped mass visible today. This means its builders were not working from an empty site. Each expansion had to carry new weight while preserving the stability of the structure beneath it. Without reinforced concrete, steel, framing, or modern geotechnical instruments, they created a platform that has remained standing for roughly 5 centuries despite monsoon rain, vegetation, stone removal, and the violent destruction of the royal capital. Exactly how the internal mass was organized remains less obvious than the external terraces suggest. The visible walls are not proof that the entire monument consists of solid, uniformly laid stone. Monumental platforms of this type could contain rubble packing, earth, secondary masonry, and retaining walls arranged in separate construction compartments. Such systems reduce the quantity of dress stone required, but they introduce another difficulty. Loose material can settle, absorb water, or push outward against the facing. The builders therefore needed to control both vertical loading and lateral pressure across a structure tens of meters wide. The platform's broad base, inward stepping profile, and thick retaining surfaces would have spread its weight gradually toward the ground. Yet no surviving Vijayanagara manual explains the calculations, construction sequence, or foundation preparation used here. The choice of material made the work even more demanding. Hampi lies within a landscape dominated by granite outcrops and immense weathered boulders, giving the builders access to durable local stone but not to material that was easy to shape. Granite is rich in hard minerals such as quartz and feldspar and cannot be carved as quickly as softer sandstone or limestone. Vijayanagara masons nevertheless produced long courses, stairways, mouldings, and extensive sculptural panels across the platform. Their likely tools included iron points, chisels, hammers and wedges, while repeated dressing and abrasion refined the surfaces. These methods are technically plausible and are consistent with wider South Indian stoneworking traditions, but archaeology has not reconstructed the precise division of labour or the time required to complete the platform's enormous carved exterior. The difficulty was not simply cutting individual blocks. Every piece had to enter a coordinated building sequence. Quarry workers first located stone without fractures severe enough to compromise it. Teams then separated blocks along natural weaknesses or prepared wedge lines, reduced unnecessary mass near the quarry, and transported the stone toward the royal centre. Even when the source lay nearby, moving multi-ton granite across uneven ground required prepared routes, timber supports, ropes, sledges, carts, or teams of draft animals. Elephants may have contributed pulling power, but popular images of elephants effortlessly lifting finished blocks oversimplify the problem. The heavier task was controlling movement so that stone did not accelerate, tilt, or crush the equipment beneath it. Raising blocks onto successive terraces presented another challenge. The most practical explanation is the use of temporary earthen ramps combined with levers and hauling systems. techniques known across many pre-industrial building traditions. Yet no intact construction ramp survives beside the Mahanavami Dibba, and no contemporary illustration shows the platform under construction. Because temporary works were normally dismantled and their materials reused, the finished monument preserves the result while concealing the infrastructure that produced it. This is not evidence of unknown machinery, but it leaves the exact logistical system unconfirmed. The platform's stairways reveal how carefully circulation was integrated into the monument. Access was provided from more than one direction, but these approaches were not simple utility stairs. They controlled how rulers, attendants, and ceremonial participants moved between levels, transforming physical elevation into a political performance. A king ascending above the crowd became visible from a great distance, while those approaching him were forced through predetermined routes. The architecture therefore functioned simultaneously as a load-bearing structure, a viewing platform, and a machine for organizing human movement. This interpretation is strengthened by the Count of Domingo Paes, a Portuguese visitor who observed Vijayanagara during the reign of Krishna Devaraya in the early 16th century. Paes described elaborate Mahanavami celebrations involving troops, horses, elephants, dancers, musicians, nobles, and royal ritual. The correspondence between these written descriptions and the reliefs carved around the platform is striking. Rows of elephants, mounted riders, hunters, warriors, acrobats, and performers turn the stone base into a permanent representation of ceremonies once staged around it. Yet the carvings create a technical mystery of their own. The scenes stretch across different construction levels and appear to have been produced by several groups of sculptors, perhaps at different times, maintaining horizontal registers, repeated proportions, and a coherent visual rhythm required more than individual artistic skill. Supervisors must have established reference lines, panel dimensions, and sequences before detailed carving began. Some reliefs were probably worked after blocks had been placed, while others may have been partly prepared on the ground. Distinguishing these stages from tool marks and unfinished surfaces is difficult, because centuries of weathering have softened many details. The imagery also suggests that the craftsmen were documenting a cosmopolitan imperial capital, rather than inventing a purely symbolic world. Camels, foreign-looking attendants, imported horses, and varied clothing styles reflect Vijayanagara's connection to commercial networks extending through the Indian Ocean and the Deccan. Horses were especially important because high-quality war animals had to be imported into southern India, where climatic conditions limited large-scale breeding. Their repeated appearance on the monument was therefore both decorative and political, advertising the empire's ability to command distant trade, military resources, and specialized knowledge. Water management forms another essential part of the engineering context. The Mahanavami Dibba did not stand alone, but belonged to a carefully organized royal landscape containing tanks, channels, drains, and ceremonial water structures. Archaeological work near the platform uncovered a precisely constructed stepped tank supplied by a stone aqueduct. Surveys across the wider Vijayanagara metropolitan region also identified wells, cisterns, and hydraulic installations serving domestic, agricultural, ritual, and public needs. These discoveries demonstrate that the royal centre was integrated into a planned water network rather than dependent only on natural runoff. For the platform itself, drainage was crucial. A structure with broad horizontal surfaces exposed to seasonal monsoon rainfall could not safely allow water to penetrate its packed interior. Saturated fill would become heavier, encourage settlement, and increase outward pressure on retaining walls. The builders therefore had to shape surfaces, joints, and surrounding ground so that rainwater escaped before causing serious damage. The survival of the main mass suggests that these measures were broadly effective, but the original drainage arrangement cannot be reconstructed completely because upper pavements, wooden structures, and adjoining buildings have disappeared, The greatest missing element remains the pavilion that once stood above the stone terraces. Post sockets and comparisons with other Vijayanagara buildings indicate that the summit probably supported columns and a roof, creating a shaded ceremonial space for the ruler and his court. Because wood is lighter than stone, it allowed a large upper structure without placing impossible loads on the platform. It was also vulnerable to fire. When the city was attacked after the Battle of Talikota, palace buildings with timber columns, beams and roof systems could be burned even when their stone foundation survived. What now appears to be an open monument was once only the lower skeleton of a far more complex architectural composition. Systematic excavations began in 1972 on the Castro de Santander hill near Canavruelas in Spain's Cuenca province. What emerged was not the Celtiberian stronghold described by the Roman historian Livy, but a later Roman city occupying a strategic promontory above the Guadiana River. Spread across approximately 20 hectares and enclosed by defensive walls, Erkavica had been laid out as a planned settlement with paved streets, houses, public buildings, and a monumental civic centre. Yet the deeper archaeologists excavated, the more difficult it became to explain how such an orderly city had been imposed upon this uneven and geologically complex hill. Livy first mentioned Erkavica during the campaign of Tiberius Sempronius Gracchus in 179 BC, describing it as a powerful Celtiberian city that surrendered after several days of resistance. The problem is that excavations at Castro de Santander have produced little material securely predating the second half of the 1st century BC. This has led some researchers to suspect that the original Celtiberian settlement stood elsewhere, possibly at Muela de Alcoche, a 37-hectare site roughly 6 kilometers upstream that is now partly affected by the Buendia Reservoir. Roman Erkavica may therefore have been an entirely new city that inherited the name and political territory of an older centre whose exact location remains disputed. That possibility makes the urban design even more remarkable. Roman Erkavica was founded ex novo, with streets arranged in an orthogonal pattern despite the fact that the hill was neither flat nor geometrically regular. Geological surveys describe the site as an elongated elevation composed of clays, sandstones and limestone beds dipping by less than 10 degrees toward the east. These materials do not behave uniformly under structural loads. Clay expands and contracts with changing moisture. Sandstone erodes along weaker layers, and limestone can fracture or channel water through hidden joints. Before a single monumental building could rise, surveyors had to decide which zones could support masonry, where slopes required modification, and how rainwater would move beneath streets and foundations. The visible city suggests that this assessment was extraordinarily effective, but no construction plan survives to show how it was achieved. Roman surveyors possessed instruments such as the groma for establishing right angles, the dioptra for measuring directions, and the chorobates for checking gradients. These devices explain the principles of Roman surveying, yet they do not reveal the exact working sequence used at Erkavica. On a hill where the natural surface constantly rises, falls, and changes composition, a regular street grid could not simply be marked out and built. Elevations had to be transferred across obstructed ground, slopes had to be cut or filled, and the alignment of one district had to remain consistent with another, even when the surveyors could not see the entire city from a single position. This challenge becomes clearest around the Forum, where architecture was used to manufacture level space rather than merely occupy it. The civic centre included a rectangular paved square, porticos, a judicial basilica, shops, and a monumental eastern extension supported by a 2-level cryptoporticus. A cryptoporticus is partly an underground structure, but at Urkavica it also functioned as an enormous artificial platform. Instead of following the hillside, the builders created a horizontal surface above it, transferring the weight of paving, columns, walls, and crowds into lower masonry that had to resist both vertical loading and lateral pressure from the surrounding ground. The engineering logic can be reconstructed in general terms, but many practical details remain invisible. The builders must have controlled the thickness of foundations, selected stones according to their position, and allowed water to escape from behind retaining structures. Otherwise, saturated earth would have increased pressure against the walls and gradually forced them outward. Yet the temporary works needed for such construction have vanished. No complete lifting system, scaffold network, or transport ramp survives, and archaeology preserves the finished platform far more clearly than the sequence that produced it. What remains is the result of calculations that were never written down at the site. The same precision appears in the residential districts. Houses were arranged within blocks defined by cobbled streets, while major routes followed the principal north-south and east-west axes. The so-called House of the Doctor was organized around an atrium with an impluvium, a sunken basin designed to receive rainwater from the roof. This familiar Roman feature was more than decoration. It formed part of a controlled hydraulic circuit in which roof geometry, gutter position, floor slope, and underground storage all had to work together. A small error in gradient could send water into adjoining rooms, undermine wall foundations, or leave stagnant pools within the house. At Urkavica, water management was not optional. The city stood on elevated ground selected for defense and visibility, not because it offered an abundant river beside every neighborhood. The Guadiella flowed below the hill, but raising large quantities of water to the settlement would have demanded sustained labor or mechanical lifting. Rainfall could be collected from roofs, courtyards, and paved surfaces, yet seasonal collection required storage capacity and careful protection against contamination. Cisterns, basins, drains, and domestic impluvia therefore reveal an integrated response, although the complete supply network has not been recovered. This uncertainty is important because the surviving hydraulic features show that the inhabitants understood water as an urban system rather than a collection of isolated structures. Streets had to shed stormwater without eroding their surfaces. Houses needed drainage that would not discharge into neighboring foundations. Public buildings required clean water while waste moved away through separate paths. Beneath this planning lay another difficulty. The hill's alternating beds of permeable and less permeable material could redirect water underground. Engineers who ignored those conditions risked creating hidden zones of saturation capable of weakening terraces and walls. The Roman solution often involved mortars made from lime, sand, and crushed ceramic material. In water-related structures, this mixture could produce opus signinum, a dense lining commonly used in cisterns, baths, channels, and pools. Crushed brick was not simply filler. Its silica and alumina-rich particles could react with lime in the presence of water, forming cementitious compounds that reduced permeability and increased long-term durability. Modern materials science describes this as a pozzolanic reaction, but the ancient builders reached the result without chemical formulas, standardized industrial kilns, or modern instruments for measuring grain size and moisture. Even so, describing the reaction does not recover the lost craft. The performance of such mortar depended on the quality of the lime, the firing temperature of the ceramic fragments, the ratio between aggregate and binder, the amount of water added, and the length of curing. Craftsmen also had to prepare the underlying surface and apply the lining before the mixture lost workability. Laboratory analysis can identify mineral phases in surviving samples, yet it cannot fully reconstruct the decisions made during construction or explain how local workshops adapted their recipes to Akavaca's climate and raw materials. Stone transport presents a related problem. Monumental public buildings required large quantities of dressed limestone and other construction material to be moved onto the hill. The final distance from a quarry may have been modest, but the last stage of the journey was the most difficult because every block had to be hauled upward. Roman builders could use sledges, rollers, wooden cranes, capstans, and coordinated teams of labourers or animals. However, those are possibilities based on wider Roman practice, not a complete reconstruction supported by surviving equipment at Akavaca. The absence of machinery does not make the construction supernatural. It reveals how little temporary infrastructure normally survives. Wooden lifting frames decayed, ropes disappeared, earthen ramps were dismantled, and metal fittings were recycled. Archaeologists are therefore left with foundations and finished masonry from which they must work backward. Tool marks can suggest how stones were shaped, while wear patterns may indicate where loads were dragged, but neither provides the full logistical chain connecting quarry, workshop, transport route, and final placement. Geophysical research has added another layer to this investigation. Electrical resistivity and electromagnetic surveys have been used to detect buried variations beneath the site, allowing researchers to identify possible walls, voids, and architectural features without excavating every area. Such methods work because stone foundations, compacted floors, and moisture-filled deposits conduct electrical energy differently. The resulting maps demonstrate that much of Akavaca remains hidden, meaning that interpretations of its streets, hydraulic network, and structural organization are still based on an incomplete sample of the city. Beneath the fields of Sakurai City in Japan's Nara Prefecture, archaeologists uncovered the remains of a settlement that appeared at a decisive moment in Japanese history. Makimuku occupied the southeastern Nara Basin near Mount Miwa, extending roughly 2 kilometers from east to west and about 1.5 kilometers from north to south. Although scattered remains had been reported earlier, the site's true scale became clear after rescue surveys in the 20th century exposed a canal-like feature approximately 5 meters wide, 1 meter deep and traceable for more than 200 meters. Later excavations revealed post holes, fences, wooden objects, ritual deposits, and unusually large buildings dating mainly from the late 2nd to the middle 4th century. Yet only a small fraction of the estimated settlement has been excavated, leaving most of its organization hidden beneath modern roads, houses, and farmland. What emerged from those trenches did not resemble an ordinary yayoi farming village. Makimuku seems to have expanded with extraordinary speed around the beginning of the 3rd century, precisely when communities across the Japanese archipelago were beginning to form larger political alliances. Earlier settlements usually developed gradually around clusters of houses, storage pits, and rice fields, but Makimuku contained dispersed architectural zones, major watercourses, and spaces apparently intended for gatherings and ceremonies. Archaeologists have therefore described it not simply as a village, but as a political and ritual center whose population may have fluctuated as people arrived from distant regions. Its sudden appearance presents the first technical mystery. Such a place required surveying, land allocation, construction schedules, and control over labor, yet no administrative records, plans, or written calculations survive. The clearest evidence of centralized planning came from a group of buildings uncovered near the center of the site. Excavations beginning in 2009 identified several structures arranged along a shared east-west axis, including the foundations of an exceptionally large raised building, estimated to have covered about 238 square meters. The post holes indicate a timber-framed hall far larger than normal domestic architecture of the period. Its position within a carefully aligned compound, together with fences and neighbouring buildings, suggests that the structures were conceived as a coordinated complex rather than added randomly over time. Some researchers have proposed that this was a palace or ceremonial residence associated with Queen Himiko, although no inscription identifies its occupant. Even without that royal interpretation, the engineering problem remains. A building of this scale required large, straight timbers, accurately spaced post holes, and a structural system capable of supporting an elevated floor and heavy roof. The builders possessed no iron machinery, powered cranes, or preserved architectural drawings. Timber could have been raised with ropes, temporary earthen ramps, and coordinated labour, but the site has preserved almost none of the temporary equipment involved. Because wood decays in the humid Japanese climate, archaeologists are left with negative impressions in the soil rather than beams, joints, or roof frames. The geometry of the foundations demonstrates that the builders could reproduce measured intervals and maintain alignment across multiple structures, while the practical methods that made this precision possible have almost entirely vanished. That lost knowledge becomes more difficult to explain when Makimuku's water system is considered. The large canal discovered during early investigations was not an isolated ditch, but part of a landscape containing natural streams, modified channels, and drainage features. Building on an alluvial fan created opportunities for access to water, but it also exposed the settlement to seasonal flooding, erosion, and unstable sediments. Channels therefore had to be positioned with sufficient gradients to carry water without rapidly cutting into their banks or leaving stagnant pools. No evidence proves that Makimuku possessed a fully integrated hydraulic grid, yet the scale of the excavated watercourse shows that substantial collective labour was invested in controlling movement through the landscape. Whether the canal primarily carried water, defined ceremonial boundaries, transported materials, or served several purposes remains disputed. The mystery deepens because Makimuku is connected to regions far beyond the Nara Basin. Pottery analysis has identified vessels or stylistic traditions associated with Tokai, Hokuriku, Sanin, Kawachi, Kibi, Omi, Kanto, Harima, the Western Seto Inland Sea, and Ki. Some published assemblages suggest that pottery with external regional characteristics formed an unusually high proportion of the material recovered from ritual areas. These objects are not merely evidence of trade. Pottery was normally heavy, fragile, and relatively inexpensive, meaning that transporting it over long distances was often less efficient than carrying rare metals or ornaments. Its presence may therefore indicate that people themselves were travelling to Makimuku and bringing familiar vessels with them. If that interpretation is correct, the settlement functioned through a logistical network extending across much of central and western Japan. Travellers had to cross mountains, rivers, and inland seas in an age without a standardized road system or written travel administration. Food, timber, and ceremonial supplies had to be gathered for assemblies whose size is unknown. Makimuku may thus preserve evidence for an early system of political coordination before the appearance of a fully documented state. Archaeology can map the origins of ceramics and compare regional manufacturing techniques, but it cannot yet reveal who organized these movements, how obligations were enforced, or whether communities participated voluntarily, through religious authority or under political pressure. Material recovered from ritual deposits shows that large gatherings were not purely administrative. An oval pit near the major building complex contained approximately 2,000 peach seeds, one of the largest concentrated deposits of its kind discovered in Japan. Excavators also recovered fish remains, including marine and freshwater species, together with more than 1,000 bones from animals such as deer, wild boar and birds. Peaches were associated with purification and protection in later East Asian traditions, while the mixture of food remains suggests repeated consumption or offerings on a considerable scale. Yet the deposits cannot establish exactly what ceremonies occurred or whether they were performed for a ruler, a deity, or a coalition of regional leaders. Makimuku's greatest demonstration of organized engineering may lie beside the settlement, rather than within its buildings. The surrounding landscape contains some of Japan's earliest monumental burial mounds, culminating in Hashihaka Kofun, a keyhole-shaped tomb approximately 280 meters long. Constructed around the middle of the 3rd century, it represents a dramatic increase in the scale of funerary architecture and is widely associated with the emergence of Yamato political power. Creating it required the excavation, transport and placement of enormous quantities of earth, along with the geometric control necessary to form a circular rear mound joined to a projecting rectangular section. Even when thousands of workers are assumed, the construction demanded coordinated surveying, standardized tasks and a reliable food supply over an extended period. This uncertainty lies at the center of the debate over Yamatai, the kingdom described in the Chinese chronicle known as the Weiji. The text records that Queen Himiko ruled a federation of communities during the 3rd century and maintained diplomatic contact with the Chinese state of Wei. Makimuku fits the general chronology and possesses the scale, ritual character and regional connections expected of a major political center. Hashihaka was also built near the period traditionally associated with Himiko's death. Nevertheless, no inscribed object naming Himiko or Yamatai has been found at the site, and the archaeological record cannot by itself prove that the Chinese name referred to this precise location. Heraclea at Latmus sits beside Lake Bafai in western Turkey, surrounded by colossal granite mountains that look almost artificial. Here, massive defensive walls climb impossible slopes, prehistoric rock paintings cover remote cliffs, and ancient water systems still survive after more than 2,000 years. Archaeologists still cannot fully explain how a city built on terrain this hostile managed to engineer stone fortifications, waterproof reservoirs, and complex infrastructure that rivaled far larger civilizations. The ruins of Heraclea at Latmus became widely studied during 19th century European archaeological surveys across Anatolia. Early explorers were shocked by the scale of the fortifications hidden among the granite formations of the Latmus Mountains. Later excavations revealed something even stranger. The region was not occupied by only one civilization. Around the city, researchers discovered prehistoric rock paintings dating back nearly 8,000 years, centuries before classical Greek settlement ever appeared there. Scientific analysis later showed that Heraclea originally stood close to the Aegean coastline. Over thousands of years, sediment carried by the Buyuk-Menderes River slowly pushed the sea away, transforming the harbour into marshland and eventually into the modern Lake Baffa region. This meant the city survived dramatic environmental changes that would have destroyed many ancient settlements dependent on maritime trade. The first major mystery of Heraclea is its location itself. Most ancient Greek cities were built on relatively manageable terrain, where transportation and construction were practical. Heraclea ignored that logic completely. The city was constructed directly among enormous granite boulders, many rising over 20 meters high, with steep inclines and unstable surfaces that remain difficult even for modern climbers. Despite this, the inhabitants built defensive walls stretching roughly 6.5 kilometers. Some sections still stand over 10 meters tall. The stones used in the fortifications weigh several tons each, yet many were fitted together with extraordinary precision. Archaeologists have compared portions of the masonry to the polygonal stonework found at Mycenae and even certain defensive sectors of Pergamon. However, Heraclea's terrain is significantly harsher. The engineering challenge becomes even more difficult when considering transportation. Ancient builders would have needed to move heavy stone blocks uphill through fractured granite landscapes without advanced machinery. Researchers estimate that some blocks required coordinated labour forces of dozens of workers. Yet there is little evidence of the wide transport roads usually associated with large-scale ancient construction projects. Some historians believe the builders used the mountain itself as part of the architecture rather than attempting to reshape it. Walls were often connected directly into natural rock formations, creating a hybrid defensive system between natural geology and human engineering. This technique resembles certain Andean fortifications in Peru more than traditional Greek urban planning. Heraclea's defensive system was not simply large, it was strategically sophisticated in ways that continue to surprise military historians. Watchtowers were positioned to maximize visibility across narrow mountain corridors and lake approaches. Instead of relying on flat defensive perimeters, the builders created overlapping observation zones using elevation differences and natural rock barriers. Modern analysts sometimes describe this as an early form of terrain-optimized warfare engineering. Certain tower positions allowed defenders to monitor enormous areas while remaining extremely difficult to attack directly. Similar principles would later appear in Byzantine mountain fortresses nearly 1,000 years afterward. Even more unusual is the way some walls curve around granite formations instead of cutting through them. This reduced construction effort while also increasing defensive unpredictability. Invading forces could not easily anticipate blind corners or elevated ambush positions. The landscape itself became part of the weapon system. The greatest technological mystery of Heraclea may not be its walls, but its survival systems. Water management in mountainous terrain is extraordinarily difficult. Seasonal droughts, shifting shoreline conditions, and unstable runoff patterns would have constantly threatened the city's population. Yet archaeological surveys uncovered an extensive network of cisterns, channels, carved reservoirs, and stone-cut storage systems integrated directly into the mountain. Some reservoirs were carved into granite itself and coated with waterproof materials that still remain partially functional today. This is one of the most debated aspects of the site. Granite is notoriously difficult to seal because microscopic fractures allow slow water leakage over time. Yet certain Heraclea reservoirs retained structural integrity for more than 2 millennia despite earthquakes, climate changes, and erosion. Researchers studying the remaining plaster layers found evidence of mineral-based waterproof compounds, possibly containing lime mixtures, volcanic additives, and finely processed aggregates similar to Roman hydraulic concrete. The comparison with Roman engineering is important because many Roman waterproof systems relied on pozzolanic ash mixtures, capable of chemically reacting with water to strengthen over time. However, Heraclea's systems appear adapted specifically for mountainous granite environments rather than coastal harbour construction. Some channels were designed to redirect runoff during heavy seasonal rains, preventing sudden flooding from destroying the city's infrastructure. Others appear connected to long-term storage systems that could preserve water through dry periods. This level of environmental adaptation suggests advanced hydrological understanding, far beyond what most people associate with smaller Hellenistic settlements. Researchers have also noted similarities between Heraclea's water systems and ancient Persian water management traditions such as Qanat engineering, where water pressure, slope control, and underground distribution were carefully calculated. Whether these similarities emerged independently or through cultural exchange remains uncertain. Perhaps the strangest detail is durability. Certain waterproof coatings survived far longer than many medieval mortars exposed to similar conditions. Some experts believe the builders may have discovered local mineral combinations uniquely suited for granite adhesion. If true, it would mean Heraclea possessed regional engineering knowledge that was highly specialized and later lost. Long before Heraclea became a Greek city, the Latmus Mountains were already sacred. Hundreds of prehistoric rock paintings discovered across the region date back roughly 8,000 years to the Neolithic era. Unlike many prehistoric sites dominated by hunting imagery, Latmus paintings frequently depict groups of humans standing together, ritual gatherings, geometric symbols, and unusual paired figures. This has led some archaeologists to propose that the mountains served ceremonial or cosmological purposes rather than purely survival-based activities. Several rock formations in the region naturally align with sunrise positions during specific times of the year. Narrow gaps between granite towers create framed solar viewing points, resembling primitive observation corridors. Although no definitive astronomical observatory has been confirmed, researchers continue investigating whether the area functioned as an early ritual landscape connected to seasonal cycles. Comparisons are often made to sites such as Chaco Culture National Historical Park and Nabta Playa, where prehistoric communities appear to have integrated landscape geometry with celestial observation. The Temple of Athena at Heraclea contains another unresolved puzzle. Some granite foundation stones display cutting marks with surprisingly straight channels and smooth surfaces. Granite ranks among the hardest natural building stones, and shaping it requires enormous effort even with iron tools. Yet several blocks appear cut with a consistency difficult to explain through primitive hammering methods alone. Similar debates exist at Baalbek, Ollantaytambo, and parts of ancient Egyptian stonework. Mainstream Astuta archaeology attributes such precision to long-term labor, abrasion techniques, and advanced craftsmanship rather than lost high technology. Still, Heraclea adds another example to the growing list of ancient sites where stone engineering appears more sophisticated than expected for the era. Another lesser-known mystery involves sound. Certain granite corridors and cavities within the Latmus Mountains produce unusually long echoes and resonance effects during strong winds or loud noises. Some researchers suspect these acoustic zones may have influenced ritual activity in the region for thousands of years. Natural amphitheatre-like formations can amplify voices across surprising distances without artificial construction. In a landscape already associated with ritual paintings and sacred symbolism, these acoustic effects may not have gone unnoticed by ancient inhabitants. Modern acoustic mapping in rocky archaeological environments has shown that many ancient ceremonial sites were intentionally selected for their sound properties. Whether Heraclea's surrounding mountains were chosen partly for this reason remains an open question. El Sheikh Hamad hides the remains of the ancient city of Dur Katlimu, a settlement that survived extreme heat, floods, earthquakes, and imperial collapse for centuries. Beneath layers of desert soil, archaeologists uncovered strange engineering systems, unusually durable mud brick structures, underground cooling chambers, and administrative records so advanced they resembled a proto-industrial logistics network. Some researchers now believe this forgotten Assyrian city possessed environmental engineering knowledge far beyond what historians once expected from the ancient Near East. The site began attracting major archaeological attention during German-led excavations in the 1970s and 1980s. Researchers identified the ruins as ancient Dur Katlimu after discovering cuneiform tablets mentioning the city directly. What initially appeared to be another mud brick settlement soon revealed something much more complex. Excavations uncovered massive storage facilities, reinforced riverbank foundations, canal systems, and thousands of administrative tablets dating between the Late Bronze Age and Neo-Assyrian periods. roughly between 1500 BCE and 600 BCE. What shocked archaeologists most was the scale of organisation. Dur-Katlimmu was not a small provincial town. At its peak, the city controlled strategic trade moving along the Euphrates corridor connecting Mesopotamia, Anatolia, and the Levant. The number of tablets recovered suggested a bureaucratic system capable of tracking grain, labour, taxation, livestock, and military supplies with astonishing precision. Some scholars compared the complexity of the city's record-keeping to later Persian administrative systems that appeared centuries afterward. The greatest engineering mystery of El Sheikh Hamad lies in its mud brick architecture. Across the ancient Near East, mud brick was common because stone was scarce and expensive. The problem is that traditional mud brick deteriorates rapidly under environmental stress. Heat expansion, seasonal flooding, groundwater salts, and erosion usually destroy these structures within centuries unless they're constantly repaired. Yet parts of Dur-Katlimmu remain standing after nearly 3,000 years. This becomes even more mysterious when considering the local climate. Summer temperatures in the region regularly exceed 40 degrees Celsius, while winter moisture and occasional Euphrates flooding create severe stress cycles in earthen materials. Under such conditions, ordinary adobe construction should fracture, soften, and collapse relatively quickly. Microscopic analysis of surviving bricks revealed unusual characteristics. Some bricks appear denser than expected, with evidence of partial vitrification on outer layers, a phenomenon normally associated with low-temperature firing. Researchers found traces of clay mixed with fine gravel, organic fibers, ash particles, and mineral-rich sediments from the Euphrates floodplain. These mixtures may have functioned similarly to composite materials, distributing stress and reducing cracking. Some engineers believe the Assyrians may have unintentionally discovered a primitive stabilization process, similar to modern soil engineering. Organic fibers inside the bricks could have acted like micro-reinforcement, while ash additives may have altered moisture absorption rates. Experimental archaeology projects comparing reconstructed Assyrian bricks with standard adobe show that treated mixtures could survive significantly longer exposure to water and temperature fluctuation. The city's walls also reveal evidence of layered construction techniques. Instead of relying on single massive walls, builders often used multiple compacted layers with alternating material density. This resembles later seismic-resistant building principles used in parts of Persia and even Incan retaining systems thousands of kilometers away. The layered design may have reduced stress propagation during earthquakes or riverbank movement. Even more puzzling is the possibility that some exterior surfaces were intentionally heat-hardened after construction. Several wall fragments display mineral transformations suggesting exposure to controlled heating temperatures between approximately 400 and 700 degrees Celsius. If intentional, this would imply large-scale thermal treatment of architecture centuries before similar methods became common elsewhere in the region. No one fully understands how ancient builders developed these techniques without modern chemistry, structural engineering, or industrial kilns. Another major mystery involves the city's hydraulic engineering. Dur-Katlimmu existed beside one of the most unpredictable rivers in the ancient world. The Euphrates could provide fertile agricultural land, but it also brought catastrophic flooding and riverbank erosion. Excavations revealed sophisticated canal networks, drainage pathways, reinforced embankments, and sediment control systems. Some riverbank foundations were constructed with alternating layers of compacted soil, gravel, and organic matter that appear specifically designed to absorb shifting pressure from floodwaters. This engineering approach resembles surprisingly modern geotechnical stabilization techniques. Similar principles are now used in flood control systems to prevent soil liquefaction and structural failure. Yet these ancient systems were built more than 2,500 years before modern hydrology emerged as a scientific discipline. Researchers also discovered evidence that water flow inside the city may have been partially regulated through elevation gradients rather than mechanical pumping. Slight changes in slope directed excess water away from residential districts while preserving underground moisture near storage areas and agricultural zones. Compared to many contemporary settlements that collapsed after repeated flooding, Dökat demonstrated remarkable environmental resilience. Among the most intriguing discoveries were underground storage chambers maintaining temperatures significantly cooler than the surrounding environment. Even during intense summer heat, these subterranean facilities remained relatively stable. Archaeologists identified ventilation shafts and airflow channels positioned to maximize passive cooling through pressure differences and thermal circulation. Modern engineers comparing the structures to later Persian yakhchals and Middle Eastern wind towers found striking similarities in airflow logic. This suggests the inhabitants may have understood fundamental thermodynamic principles through empirical observation alone. Some grain storage rooms were built partially below ground with thick insulated walls and narrow openings minimizing heat transfer. Temperature simulations indicate that these chambers could preserve food supplies far longer than ordinary surface-level storage buildings in the same climate. If accurate, this would mean the people of Dökat developed passive climate control architecture thousands of years before similar cooling concepts became widely documented elsewhere. The cuneiform tablets recovered from El-Sheikh Hamad reveal something equally astonishing. The city operated with extraordinary administrative complexity. Thousands of records documented food distribution, taxation, military movement, labor assignments, livestock inventories, and regional trade. The level of organization required for such management implies a highly efficient communication network connecting warehouses, officials, transport routes, and agricultural zones. Some historians estimate that maintaining this system would have required continuous coordination across hundreds of kilometers along the Euphrates trade corridor. This raises uncomfortable questions about how advanced Assyrian state infrastructure truly was. Traditional depictions often portray ancient empires as administratively primitive compared to later civilizations, but Dökat suggests something closer to a centralized economic control system operating on near-industrial logistical principles. The city may not have possessed advanced machinery, but it clearly possessed advanced systems thinking. The region around the Euphrates has experienced geological activity for thousands of years, yet many parts of Dökat survived for centuries. Excavations uncovered soft foundation layers made of compacted soil, gravel, and organic material beneath several of major structures. Modern engineers believe these layers may have functioned like primitive shock absorbers, dispersing vibrations before they reach the upper walls. The principle is surprisingly similar to modern earthquake-resistant engineering. This suggests ancient builders may have developed construction knowledge over generations to help structures survive in an unstable geological environment. Do you think the engineers of Dökat discovered construction techniques far ahead of their time? Or are we still underestimating how advanced ancient civilizations really were? Share your thoughts in the comments below. Located beneath the modern city of Alcalá de Henares, about 30 kilometers northeast of Madrid in central Spain, Complutum is one of the best preserved Roman cities on the Iberian Peninsula. At first glance, its streets, villas, and public buildings resemble many other Roman settlements, yet the engineering knowledge embedded beneath its stones continues to challenge archaeologists. Excavations reveal a city planned with remarkable geometric precision, supplied with clean water, protected by an advanced drainage network and decorated with wall paintings whose colors have survived nearly 2,000 years. While archaeologists understand what was built, many of the practical techniques that made it possible remain only partially explained. Complutum was known through historical references for centuries, but its true extent only became clear during systematic archaeological investigations that accelerated throughout the 20th century, particularly after urban expansion around Alcalá de Henares exposed Roman remains. Excavations eventually uncovered roughly 10 hectares of the ancient city, including the forum, residential districts, workshops, streets, drainage channels, and the famous House of Hippolytus. Ceramic analysis, inscriptions, coins, and architectural evidence indicate that the city flourished mainly between the 1st and 4th centuries AD, although earlier occupation existed in nearby settlements before the Roman urban centre was established. Every excavation has revealed a city constructed according to an organised plan, rather than one that developed gradually through centuries of random expansion. That organisation immediately raises questions because the entire urban layout follows an orthogonal grid, with streets intersecting at almost perfect right angles. The principal roads divide the city into regular insulae, while public buildings occupy carefully selected central positions connected through a coordinated transportation network. Modern surveys show that many street alignments remain astonishingly consistent, despite centuries of erosion and later construction. Roman surveyors are known to have used instruments such as the groma, chorobates, and dioptra, yet no surviving documents explain exactly how survey teams maintain such accuracy across an expanding city without optical levels, satellite positioning, or modern measuring equipment. Even a small angular error repeated over several hundred meters would gradually distort the entire plan, but Complutum displays little evidence of cumulative surveying mistakes. Archaeologists can identify the final geometry preserved in stone, yet the exact workflow used to achieve this precision remains largely invisible because the temporary wooden markers, ropes, and measuring devices disappeared long ago. The deeper researchers investigate the city, the more impressive its hidden infrastructure becomes. Beneath many streets runs an extensive drainage system built from carefully fitted masonry channels that carried wastewater away using gravity alone. Hydraulic engineering depends almost entirely upon maintaining the correct gradient, because excessive slopes increase erosion, while insufficient slopes allow stagnant water and sediment accumulation. Modern civil engineers calculate these values using mathematical models and precision instruments, yet Roman builders established stable drainage networks across an entire urban landscape nearly 2,000 years ago. Excavations demonstrate that many of these underground channels still preserve their original form, suggesting exceptionally careful construction. Archaeologists understand the physical principles involved, but cannot determine exactly how Roman engineers measured minute differences in elevation over long distances using only ancient surveying technology. The functioning network survives, while the techniques used to design it remain uncertain. The city's water supply presents an equally fascinating puzzle. Complutum possessed baths, fountains, private residences, and gardens that required reliable access to fresh water throughout the year. Archaeological investigations have identified lead pipes, ceramic conduits, cisterns, and distribution structures integrated into different parts of the city. Together, they demonstrate a sophisticated hydraulic system capable of supporting thousands of inhabitants. Yet the complete supply network has never been reconstructed with certainty. Some researchers propose connections to nearby springs through aqueducts, while others suggest a combination of groundwater extraction and local storage reservoirs. Neither explanation alone fully accounts for the flexibility implied by the surviving infrastructure. Unlike monumental aqueducts that remain visible above ground elsewhere in the Roman Empire, much of Complutum's hydraulic system vanished beneath later occupation, leaving archaeologists with isolated fragments rather than a complete engineering blueprint. As excavation expanded into elite residences, another technological mystery emerged from surfaces rather than foundations. The wall paintings preserved inside several Roman houses remain among the most remarkable discoveries at Complutum, because many still retain vivid reds, yellows, blacks, and traces of green, despite exposure to nearly 20 centuries of chemical weathering. Scientific analyses identify pigments including red hematite, yellow ochre, carbon-based black and copper-derived minerals, materials commonly used throughout the Roman world. Their composition is no longer surprising. Their extraordinary preservation is. Roman artists applied these pigments onto fresh lime plaster using the fresco technique, allowing calcium carbonate crystals formed during curing to lock the colours permanently into the wall itself. Laboratory studies confirm this mineral bonding process, yet they do not fully explain why certain murals at Complutum survived with exceptional stability while others in comparable environments deteriorated far more rapidly. Microscopic examination reveals multiple plaster layers containing carefully selected aggregates, lime and fine mineral particles, but the precise proportions, curing conditions and construction sequence that produce such durable surfaces remain impossible to reconstruct with complete confidence. Environmental factors certainly contributed, yet preservation alone cannot explain the remarkable consistency observed across several decorated rooms. The paintings therefore represent not merely artistic achievements, but evidence of sophisticated materials engineering whose practical recipes disappeared with the craftsmen who mastered them. That same attention to precision appears again in the famous mosaics of the House of Hippolytus, where thousands of tiny tesserae formed geometric patterns and marine scenes with astonishing regularity. Individual stone cubes differ only slightly in size. Curved lines remain smooth across large compositions, and spacing rarely deviates enough to disturb the overall design. Producing such consistency required careful planning long before the first tessera was placed. Archaeologists assume preliminary guidelines were drawn onto prepared mortar surfaces, yet almost no physical evidence survives because those temporary marks disappeared beneath the finished mosaic. The final artwork demonstrates exceptional geometric control, but the practical layout methods remain largely theoretical. The durability of Complutum extends beyond decoration into the buildings themselves. Many surviving walls remain remarkably stable despite almost 2 millennia of seasonal temperature changes, groundwater movement, and occasional seismic activity affecting central Spain. Excavations indicate that Roman builders adapted foundations to local geological conditions, using compacted stone, lime mortar, and carefully selected construction materials, but the exact sequence of preparation varies between structures. Some walls continue standing with minimal displacement, while neighbouring sections collapsed centuries ago, suggesting that builders modified construction techniques according to soil conditions rather than following a single standardized method. Modern archaeology can observe these results directly, but cannot always identify the engineering decisions responsible for their long-term performance, because the earliest construction phases often lie buried beneath later rebuilding. Research keeps improving our understanding of Complutum through tools like stratigraphy, ceramics, inscriptions, material analysis, and GIS. These help date the city, trace trade links, and show how it worked within the Roman world, but many questions remain. The site clearly shows what Roman engineers achieved, yet the practical know-how behind it is still unclear. Complutum is more than ruins, it's a rare glimpse of lost engineering skills that were never properly written down. Perched on limestone cliffs nearly 70 meters above the Mediterranean coast of Cyprus, Kourian archaeological site was destroyed in seconds by one of the most violent earthquakes of the ancient world. Yet beneath the collapsed columns and shattered villas, archaeologists discovered something unsettling, evidence that this city may have possessed engineering knowledge centuries ahead of its time. Modern excavations at Kourian accelerated during the 1930s under the direction of the University Museum of the University of Pennsylvania. What researchers uncovered was extraordinary. Entire districts frozen in the exact moment of destruction, caused by the massive earthquake of 365 AD, an event now estimated between magnitude 8.0 and 8.5. Bodies remained trapped beneath collapsed roofs. Stone columns had fallen in identical directions. Mosaics survived while surrounding walls disintegrated, and even today, Kourian remains one of the clearest archaeological earthquake snapshots ever discovered in the Roman world. The first mystery of Kourian begins with its location itself. The city was constructed directly above unstable coastal cliffs within one of the most seismically dangerous regions in the eastern Mediterranean. Cyprus lies near the boundary between the African and Eurasian tectonic plates, where stress accumulation has triggered destructive earthquakes for thousands of years. Modern geological surveys show the limestone beneath Kourian contains natural fractures capable of amplifying seismic waves. Under ordinary engineering logic, this should have made the site unsuitable for large stone architecture. Yet for nearly 700 years, Kourian supported massive Roman bath complexes, multi-story villas, aqueduct systems, granite columns weighing several tons, and a theatre capable of holding around 3,500 spectators. What confuses researchers is how the city remained structurally stable for centuries despite constant tectonic instability. Some engineers now believe the builders of Kourian understood practical earthquake behavior through long-term observation rather than mathematics. Similar patterns appear in ancient earthquake-resistant structures elsewhere in the Mediterranean, including Parthenon, Temple of Apollo at Delphi, and Pont du Gard. But Kourian may represent one of the most advanced examples, because the entire city functioned on unstable coastal geology. One of the strangest discoveries at Kourian involves the way its buildings absorbed seismic force. Archaeologists found that many stone blocks were not rigidly cemented together. Instead, certain columns and foundation layers used flexible contact zones, allowing slight movement during tremors. In modern engineering, this resembles primitive seismic isolation systems. Some foundations contained alternating layers of crushed stone beneath heavier masonry, and these layers may have acted as shock absorbers, dispersing energy before it reached upper structures. The same principle appears in modern anti-earthquake architecture used in Japan and California. The theatre of Kourian is especially puzzling because despite repeated earthquakes over nearly 2 millennia, much of its curved seating structure survived remarkably well compared to nearby rectangular buildings. Researchers studying ancient structural mechanics noticed several unusual features. Curved geometry distributed stress more evenly, stone seating rows acted as interlocking stabilizers, and open-air construction reduced roof collapse pressure. Even more mysterious is the precision of the load distribution. Modern simulations suggest some sections of Kourian's architecture approach stability ratios comparable to later Byzantine seismic designs developed centuries afterward. No surviving Roman texts fully explain how such engineering knowledge was standardized. Kourian ancient theatre is not only structurally strange, it also possesses unusually advanced acoustic behavior. Today, visitors standing at the center of the stage can still be heard clearly from the upper seating rows, despite intense sea winds from the Mediterranean coast. Acoustic tests conducted at similar Greco-Roman theatres show speech intelligibility often remains above 90% across large seating areas without amplification. At Kurion, the geometry appears almost mathematically optimized. The semicircular arrangement minimizes echo distortion. Limestone surfaces reflect mid-frequency human speech efficiently, and the slope angle enhances sound projection naturally. What makes this mysterious is that the theatre predates formal acoustic science by more than 1,000 years. Ancient architects seemingly achieved sophisticated sound engineering entirely through empirical experimentation. Comparable acoustic anomalies exist at Epidaurus Ancient Theatre and Aspendos Theatre. Yet Kurion's exposure to ocean winds should theoretically reduce clarity significantly. Instead, the site still produces highly intelligible sound conditions even today. The greatest mystery of Kurion lies inside the house of Eustolios. More than 1,500 years after the earthquake, many mosaics still preserve astonishing color intensity, despite exposure to moisture, salt air, temperature fluctuations, and structural collapse. For conservators, this should not happen. Scientific analysis of the mosaics revealed several extraordinary characteristics. Mineral pigments contained unusually stable iron oxides and copper-based compounds. Lime mortar layers displayed extremely low salt penetration, and tesserae placement reduced internal cracking during seismic vibration. Some sections maintain visible detail after surviving conditions that normally destroy Roman floor art within centuries. Researchers comparing Kurion's mosaics to those at Pompeii Archaeological Park, Villa Romana del Casale, and Antioch Mosaic Museum notice something unusual. The mortar beneath Kurion's mosaics appears exceptionally resistant to both humidity and microfracturing. Modern laboratory studies suggest the lime mixture may have undergone prolonged chemical curing, similar to advanced Roman marine concrete. Some samples contain microscopic crystalline bonding structures that strengthen over time when exposed to moisture. This has led to speculation that builders in Kurion possessed localized material formulas now completely lost. Even more mysterious is how certain mosaic panels survived intact while surrounding stone walls collapsed entirely during the 365 AD earthquake. Some researchers suspect the flooring system itself distributed seismic stress differently from vertical masonry. In other words, the mosaics may not only have been decorative, they may also have been engineered for structural resilience. The destruction layer of 365 AD remains one of the most important earthquake records in archaeology. The earthquake likely originated near Crete and generated a massive tsunami across the eastern Mediterranean. Ancient historian Ammianus Marcellinus described entire coastlines being devastated. At Kurion, evidence suggests the shaking intensity reached catastrophic levels. Columns snapped at their weakest stress points. Roof beams collapsed almost simultaneously. Human remains indicate many inhabitants died instantly, and entire residential sectors were abandoned afterward. Yet the destruction pattern remains inconsistent. Some areas were pulverized, while others survived surprisingly well only meters away. Modern geophysicists believe this may involve seismic wave amplification caused by cliff edge resonance, a phenomenon where certain geological formations magnify earthquake energy unpredictably. This effect has also been documented during modern earthquakes in Mexico City and parts of Turkey. But Kurion presents one of the oldest known examples preserved archaeologically. Supplying water to a city built on unstable cliffs should have been nearly impossible, yet excavations uncovered a remarkably advanced hydraulic system, including ceramic pressure pipes, gravity-fed reservoirs, sediment control basins, and water distribution channels maintaining steady flow across uneven terrain. The precision of pipe alignment is especially impressive. Some ceramic sections fit together with millimeter-level accuracy despite being produced nearly 2,000 years ago. Even modern engineers acknowledge that maintaining hydraulic stability in seismic coastal terrain remains extremely difficult. What is astonishing is that parts of Kourion's water infrastructure survived multiple earthquakes before the final destruction. Do you think Kourion was abandoned because of fear, religion, or because its ancient engineering knowledge was permanently lost? Share your thoughts in the comments below. Halmaris is located at the edge of the Danube Delta, a region defined not by stability but by constant transformation. Rivers shift, sediments accumulate, land appears and disappears over decades. It is precisely the kind of environment where permanent architecture is expected to fail, and yet Halmaris did not. The site first entered modern historical awareness in the 19th century through scattered references and surface observations, but systematic excavations only began in the late 20th century. Early surveys identified defensive walls, towers, and traces of Roman military occupation. Later excavations revealed far more: a basilica, a crypt, and stratified occupation layers indicating continuous use from the 1st century CE into the Byzantine period. Each campaign added detail, but also deepened the central contradiction this was not a temporary outpost. It was a long-lived, structurally stable settlement built in one of the least stable environments in southeastern Europe. Initial excavations uncovered the fortification system, stone walls several meters thick, reinforced towers, and carefully designed entry points. Subsequent campaigns revealed a Christian basilica constructed in the 4th century, followed by the discovery of a crypt containing 2 skeletons attributed to the martyrs Epictetus and Astian. Later studies identified evidence of water proximity sediment layers, geomorphological patterns, and structural orientation suggesting that Halmaris once had direct access to navigable waterways. Each discovery expanded the site's function, military, religious, and possibly commercial. But none resolved the fundamental problem. How did it persist here at all? The first and most significant mystery lies in its location. Roman engineering was not random. Across the empire, fortresses were strategically placed based on elevation, defensive advantage, and geological stability. Sites like Vindolanda or the forts along Hadrian's Wall were constructed on firm ground, often elevated, minimizing long-term structural risk. Halmaris violates this pattern completely. It sits within a deltaic environment characterized by alluvial soils, fine-grained sediments with high water content, low cohesion, and a well-documented tendency towards subsidence. Modern geotechnical studies show that such soils can shift measurably within decades. Over centuries, the effect compounds dramatically. To quantify this, deltaic subsidence rates in comparable environments can reach several millimeters per year. Over 500 years, that translates into vertical displacement on the order of 1 to 2 meters, more than enough to destabilize stone foundations. And yet, the walls of Halmaris remained intact long enough to support continuous occupation across multiple centuries. There is no surviving documentation describing specialized foundation techniques, no evidence of deep piling systems comparable to later Venetian engineering, and no clear indication of artificial ground stabilization. The archaeological record shows adaptation and repair, but not the kind of foundational innovation required to fully explain such longevity. This creates a structural paradox. Either the Romans employed localized engineering solutions that have left no clear trace, or the environmental conditions during the occupation period were significantly different from those observed today. Paleogeographic studies suggest that the Danube Delta has undergone major shifts over the past 2 millennia, but even reconstructed ancient shorelines do not fully resolve the instability problem. The fortress was still built in a marginal zone, an area where long-term settlement would typically be avoided. What makes this even more unusual is that Roman military planning was typically conservative, favoring predictability over experimentation. Halmaris, by contrast, behaves like an exception that should not exist within that system. The second anomaly concerns the scale and intensity of fortification. Halmaris was not a lightly defended outpost. Its walls, towers, and internal layout indicate a level of military investment comparable to far more strategically critical sites. Yet historically, this region was not the primary axis of major Roman conflicts. Compared to heavily contested frontiers like the Rhine or the main Danube line further west, Halmaris appears overbuilt. Defensive architecture generally reflects threat level. Here, the architecture suggests either a threat that was never recorded or a strategic importance that has been underestimated. The disproportion between location and defensive strength creates a mismatch that remains unresolved. The third layer of complexity emerges with the basilica and the crypt. The transformation of a military site into a religious center is not unusual in late antiquity, but the prominence of the basilica at Halmaris suggests more than routine conversion. The attribution of the remains to Epictetus and Astion is based on later textual traditions rather than direct scientific confirmation. Radiocarbon analysis places the remains within a broadly compatible timeframe, but not with sufficient precision to conclusively verify identity. More importantly, the presence of such a site implies that Halmaris held symbolic or spiritual significance beyond its military function. Why this location, remote, unstable, and marginal, became a focal point for early Christian memory remains unresolved. Another unresolved question involves its relationship to water. Geological and sedimentary evidence indicates that Halmaris was once connected to a navigable branch of the Danube or a nearby lagoon system. If true, this would partially explain its strategic value control over a fluid, shifting water network. However, no intact harbour structures have been definitively identified, and the ancient hydrological configuration remains partly speculative. The delta has reconfigured itself multiple times since antiquity, erasing direct evidence and leaving only indirect traces. This raises the possibility that Halmaris was once far more connected and far more important than its present inland position suggests. Finally, there is the question of abandonment. Many Roman sites show clear signs of violent destruction, economic collapse, or environmental catastrophe. Halmaris does not. The archaeological layers suggest gradual decline rather than sudden collapse. Occupation diminishes, structures fall into disuse, and the site is eventually left behind. There is no single catastrophic event, only a quiet disengagement. This pattern complicates interpretation because it removes the most common explanatory frameworks. Without a clear ending, the site resists being placed into a familiar historical narrative. Taken together, Halmaris does not present a single mystery, but a convergence of them. A fortress built where it should not stand, a structure that persists where it should fail, a defensive system that exceeds apparent necessity, a religious center emerging in an unlikely place, a settlement connected to waterways that no longer exist, and an ending that offers no clear cause. Individually, each of these anomalies might be explained: environmental fluctuation, strategic miscalculation, religious reinterpretation, gradual economic decline. But combined, they form a pattern that resists simple explanation. Halmaris does not contradict Roman engineering. It exposes the limits of what we currently understand about how that engineering was applied in extreme conditions. And that leaves a final question unresolved. If a site like Halmiris could exist, function, and endure for centuries under conditions we consider unsuitable, how many other places have followed the same pattern and simply disappeared without leaving enough evidence behind to challenge our assumptions? The ruins of Cherven Fortress rise above the limestone cliffs of northeastern Bulgaria, like the remains of a vanished military machine. Archaeologists believe the fortress reached its peak during the Second Bulgarian Empire in the 13th and 14th centuries, controlling major trade and military routes across the Balkans. But what transformed Cherven from a forgotten medieval ruin into one of the region's greatest engineering mysteries was not simply its age or destruction. It was the discovery that nearly every part of the fortress appears to solve technical problems that should have been almost impossible for its era. Massive defensive walls were anchored directly into unstable cliff rock. Sophisticated water systems operated hundreds of feet above the river below. Multi-layered fortifications showed structural logic similar to far later military architecture, and some construction materials have survived for more than 7 centuries with a durability researchers still struggle to fully explain. The site was first systematically investigated during the late 19th century after local scholars reported unusual stone ruins spread across the plateau. Early excavations revealed towers, churches, underground passages, workshops, streets, and enormous defensive walls extending across the cliff edges. Archaeologists eventually discovered that Cherven once covered more than 1 square kilometre and may have housed several thousand inhabitants during its peak. What shocked researchers most was the complexity hidden beneath what initially appeared to be a simple medieval fortress. The deeper they excavated, the more the site resembled a highly engineered defensive city, carefully adapted to an impossible landscape. The first major mystery involves the terrain itself. Cherven was built on fractured limestone plateaus overlooking deep valleys nearly vertically cut into the landscape. Even with modern machinery, constructing a stable fortified city on such terrain would be extremely difficult. Yet medieval builders somehow created flat structural platforms, aligned walls with remarkable precision, and distributed enormous weight across unstable rock formations. Some surviving walls remain surprisingly straight despite centuries of earthquakes, erosion, freezing winters, and temperature expansion. Archaeological surveys show that many foundations were not simply placed on rock, but actually interlocked into carved bedrock channels. This technique dramatically increased stability and prevented lateral collapse. Engineers comparing Cherven to other mountain fortresses estimate that thousands of tons of stone had to be transported uphill without modern lifting systems. Some individual blocks weigh several hundred kilograms. The precision of these constructions becomes even more puzzling when compared to the technology available during the 13th century. Medieval Balkan builders primarily relied on iron chisels, wooden cranes, ropes, sledges, and animal labor. Yet several wall sections display alignment errors of only a few centimeters over long distances. Similar precision is often associated with much later military engineering traditions. Researchers have compared the logistical difficulty of Cherven's construction to sites like Machu Picchu and Masada, both famous for solving impossible architectural challenges in extreme terrain. But the greatest mystery of Cherven may be water. The fortress sits approximately 200 meters above the river below, yet historical evidence suggests the city could survive prolonged sieges involving thousands of people. Medieval armies often relied on cutting water access to destroy elevated fortresses, but Cherven appears to have developed unusually advanced solutions to this problem. Excavations uncovered reservoirs carved directly into bedrock, underground cisterns, ceramic pipe fragments, drainage systems, and channels designed to collect and store rainwater. Some cisterns remain partially waterproof even today. Researchers attempting to calculate the fortress's water supply encountered a serious problem. Average rainfall in the region appears insufficient to sustain the estimated population during long military blockades. This has led to theories that additional underground water systems remain undiscovered beneath the fortress. Ground-penetrating radar surveys have identified several buried anomalies that may represent tunnels or concealed chambers connected to hidden reservoirs. Some archaeologists believe Cherven may have employed gravity-fed hydraulic systems similar to those seen in Byzantine engineering centres. Others suggest deep vertical wells could still exist beneath collapsed structures. The waterproofing material inside certain reservoirs presents another unexplained puzzle. Chemical analysis suggests mixtures of lime mortar combined with crushed ceramics and mineral additives. This resembles ancient hydraulic concretes used by the Romans and Byzantines, materials specifically engineered to resist moisture penetration. Some samples display crystalline bonding patterns that continue strengthening over time, similar to self-healing reactions identified in Roman marine concrete. If confirmed, this would suggest that builders in medieval Bulgaria possessed advanced empirical knowledge of long-term material durability that was never formally documented. The fortress towers themselves reveal another astonishing level of engineering sophistication. The central defensive tower, one of Cherven's most recognizable structures, contains unusually strategic wall reinforcement patterns. Rather than maintaining uniform wall thickness, builders concentrated heavier masonry in zones most vulnerable to attack or structural stress. Modern structural engineers note that this resembles load distribution principles used in far later military fortifications. Some internal layers alternate between brick and stone, possibly helping absorb impact energy from siege weapons. During the 13th and 14th centuries, trebuchets capable of launching projectiles weighing over 100 kilograms were becoming increasingly common across Europe and the Middle East. Cherven's architecture appears specifically optimized to resist these forces. This raises a difficult historical question. How did local builders acquire such sophisticated engineering knowledge? Very few surviving texts describe the technical construction methods used at Cherven. Some historians believe Byzantine military engineers may have transferred advanced architectural concepts into Bulgaria during periods of political alliance and warfare. Others argue the fortress represents centuries of accumulated regional experimentation, gradually refined through conflict. Yet much of this knowledge vanished after the Ottoman expansion into the Balkans during the late 14th century. Another major mystery surrounds the durability of the masonry itself. Many surviving structures have endured over 700 years of rain, frost cycles, earthquakes, biological growth, and thermal stress. Some mortar joints remain surprisingly intact despite complete exposure to the environment. Laboratory analysis indicates unusually fine particle distribution within the mortar mixtures, allowing tighter bonding between stone layers. Certain walls also contain hidden brick inclusions, acting almost like internal shock absorbers. Comparisons with other medieval European fortresses reveal that Cherven's preservation is unusually strong considering the harsh climate conditions of northeastern Bulgaria. Winter temperatures in the region frequently fall below freezing, causing repeated expansion and contraction inside stone cracks. Over centuries, this process destroys most exposed masonry. Yet parts of Cherven continue standing at heights exceeding 10 meters. Researchers suspect builders intentionally designed drainage systems inside the walls themselves, preventing trapped moisture from accumulating and freezing internally. Similar anti-moisture engineering techniques appear in some late Byzantine fortifications, but remain poorly understood. Archaeologists discovered that Cherven was far more than a military fortress. Excavations revealed churches with frescoes, workshops, metal production areas, storage facilities, homes and paved roads. The city was organized into layered defensive zones, allowing defenders to retreat upward into safer sectors during attacks without losing the entire fortress. This resembles early forms of defense in depth, long before such military strategies became common. Even more mysterious are the underground spaces that remain largely unexplored. Surveys detected hidden voids beneath collapsed structures, possibly leading to escape tunnels, storage chambers, or additional water systems. Because much of Cherven still has not been excavated, the fortress continues revealing new mysteries even today. Do you think the builders of Cherven possessed engineering knowledge far beyond what historians believe medieval societies were capable of? Share your thoughts in the comments below. Cabezo Redondo is not supposed to function the way it does. Located near modern Villena in southeastern Spain, this hilltop settlement dates to approximately 2000 to 1200 BCE. Within the Iberian Bronze Age, a period typically defined by small, loosely organized communities still experimenting with early forms of social complexity. Yet from the moment it is examined in detail, Cabezo Redondo resists that classification. It appears structured, controlled, and internally coordinated at a level that does not align with its time. Excavations carried out throughout the 20th century revealed a densely compressed settlement built across a naturally defensive elevation. The architectural layout is not random. Houses are tightly interlocked, sharing walls and minimizing unused space. Movement is channeled through narrow, deliberate pathways. This is not organic expansion. It resembles a system under constraint, as if spatial efficiency was not a byproduct, but a governing principle. Compared to other Iberian Bronze Age sites, particularly the dispersed rural settlements across central Spain, Cabezo Redondo behaves less like a village and more like an early compact urban mechanism. The anomaly intensifies when storage systems are considered. Archaeologists uncovered numerous silos and embedded storage pits integrated directly into domestic structures. Their combined capacity exceeds what would be expected for a subsistence-level population. Estimates indicate volumes sufficient either to sustain a significantly larger population than the settlement likely contained, or to maintain reserves far beyond seasonal necessity. This is not casual surplus. It implies intentional accumulation, long-term planning, and controlled distribution, which leads to the central problem: control without visibility. No palatial structures have been identified. There are no monumental administrative buildings, no centralized complexes that would indicate a ruling authority in material form. In contemporaneous sites such as Mycenae, we observe massive fortifications, formalized elite spaces, and unmistakable symbols of hierarchy. Cabezo Redondo presents none of these. And yet, the internal logic of the settlement suggests that hierarchy must have existed. Certain dwellings are larger and more complex, implying social differentiation. Storage appears unevenly distributed, implying selective access. The system operates like a managed economy, but without exposing the mechanism that manages it. Material culture reinforces the contradiction. The inhabitants clearly possessed bronze working capabilities, a technology dependent on both technical knowledge and access to trade networks for copper and tin. While parts of Iberia provide certain metal resources, the full metallurgical process requires connections beyond the immediate environment. This suggests participation in regional or even long-distance exchange systems. However, the scale of coordination implied by the settlement's organization exceeds what is typically supported by evidence of such networks in this region during the same period. Once again, the internal complexity of the system outpaces its external context. Nearby, another discovery complicates the picture further: the Vilena treasure. This hoard, consisting of nearly 10 kilograms of gold along with silver and early iron objects, is one of the most significant Bronze Age finds in Western Europe. The craftsmanship is precise. The quantity is extraordinary. Yet within Cabezo Redondo itself, there is no equivalent display of wealth, no elite tombs filled with gold, no ceremonial architecture designed to exhibit power. The wealth exists, but it is disconnected from visibility. This creates a second layer of contradiction. In most early complex societies, wealth is transformed into display. It legitimizes authority, reinforces hierarchy, and communicates dominance across social layers. At Cabezo Redondo, wealth appears to have been removed from this equation. It is accumulated, but not exhibited, controlled, but not declared. The system does not signal power in the ways we expect. Architecturally, the settlement reflects a form of intelligence that is subtle but effective. Construction relies on stone and mud brick, materials used with an efficiency that maximizes thermal regulation and structural stability. The design integrates seamlessly with the terrain, reducing the need for large-scale defensive construction while maintaining security. This is not technological limitation, it is optimization. Yet the tools recovered from the site do not fully explain the precision of spatial organization achieved. The knowledge existed, the process remains partially obscured. Population estimates suggest a few hundred inhabitants at peak occupation. Statistically, this is significant. Anthropological models indicate that such a population size typically does not require nor sustain the level of organizational complexity observed here without either strong centralized authority or a much larger demographic base. Cabezo Redondo fits neither model cleanly. It is too small to demand such coordination, yet too coordinated to arise spontaneously. Time introduces the final disruption. The settlement remained active for several centuries. There is no clear evidence of catastrophic destruction, no widespread burn layers, no mass graves indicative of conflict, no abrupt abandonment horizon. Instead, occupation appears to diminish gradually. Activity declines, structural coherence weakens, and eventually, the system ceases to exist. Not destroyed, not conquered, simply discontinued. This pattern diverges from better documented collapses. Across the Eastern Mediterranean, late Bronze Age sites frequently display clear destruction layers associated with systemic collapse around 1200 BCE. Cabezo Redondo does not conform to this pattern. Its disappearance appears internal, slow, and unforced. What remains is not a typical settlement, but a functional anomaly, a community that demonstrates controlled resource management, spatial precision, and social differentiation without the visible frameworks that usually support such features. It behaves like a system governed by principles that are only partially preserved in the archaeological record. One interpretation suggests that Cabezo Redondo represents an early form of centralized economic control authority, embedded not in monuments, but in access to storage and distribution. Another proposes that social cohesion and shared cultural norms replace the need for overt displays of power, creating a stable equilibrium that left minimal physical evidence. Both interpretations attempt to reconcile the data. Neither fully resolves it. A more unsettling possibility remains. Cabezo Redondo may represent a configuration of human organization that does not align with established models of social evolution. A system that functioned efficiently within its own constraints, but did not expand, replicate, or leave a clear developmental legacy. Not an early step toward later civilizations, but a parallel formation, one that emerged, stabilized, and then ended without continuation. Because the central issue is not the absence of information, it is the behavior of the information we possess. The settlement is too organized for its scale, too controlled for its visibility, and too coherent for its historical position. It does not follow the expected trajectory of complexity. Cabeza Redondo does not revise history. It exposes the possibility that history itself is incomplete. Hidden within the desolate expanse of the Great Basin in western Nevada, Spirit Cave stands as one of the most quietly disruptive archaeological sites in North America, a place where fragile strands of plant fiber challenge everything we thought we understood about prehistoric technology. First excavated in 1940 by Sidney M. Wheeler, the cave initially gained attention for the discovery of a remarkably well-preserved human mummy, later dated to approximately 10,600 years before present through radiocarbon analysis. Yet as subsequent expeditions revisited the site, particularly in the 1970s with improved stratigraphic methods, in the 1990s with refined carbon dating, and again in the 2010s using advanced material analysis, the true significance of Spirit Cave began to shift away from the human remains themselves and towards something far more subtle, yet arguably more profound: the textiles, sandals, and woven artifacts that accompanied them. These items, crafted from processed sagebrush bark and other native plant fibers, have been dated to roughly the same period, placing them among the oldest surviving examples of fiber technology in the Americas and possibly the world. What makes them extraordinary is not merely their age, but the level of technical precision embedded in their construction, a precision that seems almost anachronistic when placed within the broader context of early Holocene hunter-gatherer societies. The sandals recovered from the cave, for instance, are constructed using a sophisticated twining technique in which two or more weft elements are systematically twisted around a series of warp elements, creating a flexible yet highly durable structure. Microscopic analysis has revealed that the fibers were not randomly assembled but processed to achieve consistent thickness and tensile strength, with twist angles maintained at near uniform degrees across entire sections of the weave. In some cases, the spacing between strands remains consistent within a fraction of a millimeter, suggesting not only skilled craftsmanship, but an internalized standard of production, something closer to an unwritten engineering protocol than ad hoc experimentation. Experimental reconstructions conducted by modern researchers have demonstrated that reproducing these sandals using only primitive tools requires dozens of hours of labor and a deep familiarity with the mechanical behavior of plant fibers, including their response to moisture, tension, and repeated stress. When compared to early textile traditions in other parts of the world, the implications become even more striking. At sites like Çatalhöyük, widely regarded as one of the earlier centers of complex human settlement, evidence of woven textiles appears around 7000 BCE, several millennia after the Spirit Cave artifacts, yet often in less structurally refined forms. Similarly, early Neolithic sites in the Levant and Mesopotamia show the gradual emergence of weaving technologies alongside the development of agriculture and sedentary life, reinforcing the long-held assumption that complex textile production is a byproduct of stable, resource-rich societies. Spirit Cave, however, disrupts this narrative entirely. Here, in a harsh, resource-scarce desert environment inhabited by mobile hunter-gatherers, we find fiber technologies that not only rival, but in some respects exceed those of later agricultural communities. This raises a fundamental question. How did such a high level of material engineering emerge in a context where, according to conventional models, it should not exist? The answer may lie in the unique environmental pressures of the Great Basin, with extreme temperature fluctuations, near limited water sources, and a landscape that offers little margin for error, survival would have depended on tools and materials that were both lightweight and exceptionally durable. In this context, the development of advanced fiber technologies may represent a form of adaptive innovation, a response to environmental constraints that drove experimentation and refinement over countless generations. Yet even this explanation falls short of accounting for the apparent standardization observed in the artifacts. The repeated patterns, consistent techniques, and uniform quality suggest not isolated ingenuity, but a shared body of knowledge, transmitted and preserved within the community with remarkable fidelity. Without written language, this transmission would have relied on oral instruction and hands-on apprenticeship, raising the possibility that prehistoric societies possessed far more sophisticated systems of knowledge preservation than we typically acknowledge. Further complicating the picture is the role these textiles may have played beyond mere utility. The spirit cave mummy itself was found wrapped in layers of woven material, arranged in a manner that appears deliberate rather than incidental. Some researchers have proposed that these wrappings were designed not only for cultural or ritual purposes, but also to regulate the microenvironment around the body, controlling airflow, reducing moisture, and inhibiting microbial activity. If true, this would imply an empirical understanding of how organic materials interact with environmental conditions, effectively representing an early form of biomaterial engineering. And such a possibility is supported by the exceptional state of preservation observed in both the mummy and the associated artifacts, which show minimal signs of decay despite their immense age. Modern analytical techniques, including scanning, electron microscopy, and chemical residue analysis, have begun to explore whether the fibers were treated with natural compounds, such as plant resins or ash solutions, to enhance their durability or resistance to pests. While definitive conclusions remain elusive, preliminary findings suggest that at least some level of material processing may have been involved, hinting at a proto-chemical approach to textile production. When viewed in this light, the artifacts of Spirit Cave are no longer simple remnants of daily life, but components of a broader technological system, one that integrates material science, environmental adaptation, and cultural practice into a cohesive whole. And yet, perhaps the most perplexing aspect of this system is its apparent disappearance. Despite the sophistication evident in the Spirit Cave materials, similar techniques do not appear to persist in a continuous, traceable lineage within the archaeological record of North America. Later cultures in the region exhibit their own forms of fiber technology, but often with different methods, materials, and levels of refinement, suggesting either a loss of knowledge or a transformation so complete that its origins become unrecognizable. Yet this discontinuity challenges the idea that technology evolves in a straight line, suggesting that entire bodies of ancient knowledge may have emerged and disappeared without leaving clear traces. Spirit Cave therefore acts both as a window into the past and a warning that what archaeology preserves is only a small fragment of true history. The woven artifacts found inside are not just objects, but evidence of a sophisticated and forgotten knowledge system, proving that prehistoric humans may have reached levels of technical mastery far beyond what we once believed. And the lingering question remains, how many ancient technologies have been lost simply because they were never carved in stone? If such advanced textile and material technologies existed over 10,000 years ago and then almost completely disappeared, how many other ancient technologies might we have never discovered? Share your thoughts in the comments below.